All right. Well, thanks everybody for joining. Sorry for the quick little technical difficulties there, but hopefully we're good to go now. Appreciate you all joining. We're going to talk today about a pretty new subject, something that has emerged from the Bay Area tech companies within the last 5 years and seems to be sort of the next evolutionary step of platform engineering after DevOps, which is we call developer productivity engineering. Companies like LinkedIn, Netflix, Twitter, Uber, Square, they've been practicing this stuff at scale for about 5 years, right? And now you're starting to see some of the larger enterprises and less tech companies starting to adopt these policies as well. So we're going to talk about what it is, we're going to talk about why it is, and then we're going to dive into some specific technologies that we recommend as part of this practice. So the first part of this lecture is going to be sort of theory, talking about the state of productivity as we are right now. And then we're going to dive into a more technical talk about the individual technologies and process that we recommend as part of developer productivity engineering. Some of the screenshots that you will see and a little bit of the demo, assuming that this thing behaves, is going to demonstrate the Gradle Enterprise product, but this is not a sales pitch for Gradle Enterprise, okay? There are plenty of ways that you can achieve the same things, gather the same data, accelerate your feedback cycles without using our product, right? I'm not a salesperson. We have salespeople at Gradle. I'm an evangelist of this practice, which is a vendorless practice. Hello. Having all kinds of issues. There we go. So yeah, I'm Justin REOCK, Chief Evangelist, Field CTO at Gradle. My background is in software development. I spent a long portion of my career writing code and then moved into more enterprise architecture, then was running teams of enterprise architects, and then at some point I started doing more PowerPoint, and that's kind of what I do now. So you could consider me sort of an advocate. I run the team of advocates at Gradle. We have 4 folks on that team right now. Some of you may be familiar with them. They're pretty well known. We have Trisha G, who came to us from JetBrains. We have Baruch Sadegorski, who came to us from JFrog. Brian Demers, who came to us from Okta, and before that Sonatype, and is a major Maven DevRel. And then we have Vincent Mayers, who runs the Atlanta Java User Group and the DevNexus conference that just happened last week. So I run that team and also help with other stuff in the organization. But today we're just here to talk about this. So to set the stage and give some context, I want to talk to you about the myth of the 10x developer. Anybody familiar with that term, 10x developer, right? So it's a total myth within a single organization. And we're going to look at some compelling data that kind of makes that case. But then we're going to talk about how organizations actually can be 10x, right? So where did this myth come from? Every myth has a kernel of truth to it, right? It probably came from this study that was launched in the mid-'80s called the Coding War Games. 2 folks, authors, Tom DeMarco, Timothy Lister, divided a study that they called the Coding War Games. And this was executed from 1984 to 1986. More than 600 developers from over 92 companies took part in this study. And the purpose was to discover the best and the worst traits of developers. The competition unit was a pair of programmers from the same organization, but they were not peered, right? They were not working together on the task, right? They were sort of competing with one another within the same organization. A program specification, a business task was fixed, and the participants were asked to log their time, log how much time it took for them to complete the task, right? So pretty simple. They used their own workspace. They used their own preferred language. There was no enforcing, hey, you must use this language or you must use this framework. Just whatever you would normally do. Just perform the task doing your normal routine. You can see the output of this study here, and I'll make sure that, I don't know how that works with the slides, but you can either, if the conference organizers don't distribute them, then you feel free to reach out to me directly and I can get them to you. But you can see the results of that study here. It would also fold into this book, Peopleware. Anybody read Peopleware before? If you were at all interested in building highly productive software teams, This is the book. It still holds up. It's in its third revision now, but it's still one of the best books, I think, in terms of teaching what are the best practices for building highly productive software teams. And it's these two authors who launched this study that wrote this book, and the book centers around the outcome of this study. All right. So the best programmers outperform the worst by roughly a 10-to-1 ratio. Okay, so again, this is probably where the myth sort of originated. Before we get into why that doesn't actually matter in a single organization, let's talk about some interesting non-factors. What were some things that actually didn't factor into productivity? Language. Very interesting here. Didn't really matter which languages, with the exception of assembly. Those poor assembly programmers, they took a little longer. But for the later generation languages, not really much of a difference statistically in terms of productivity. This one's a hard pill to swallow. Years of experience didn't really matter either. Whether you had 2+ years of experience or 10 more years of experience, you were producing at roughly the same rate. The drop-off happened at around 6 months of experience. Number of defects. Okay, so are you just like cranking out code really fast, but it's terrible, buggy code? No. The top performers created defectless code. They didn't have any bugs in their code. And then another bitter pill, salary. The top performing developers were only making about 10% more on average than the bottom performing developers. So what did matter? All right, well, here's where things get really interesting. Peered programmers within the same organization performed at basically the same level, right? There was only a 21% differential between participants, and when you look at the fact that the top performing organizations were actually over 11 times more productive than the bottom performing organizations, that 21% becomes statistically insignificant. So what does this say? It's within the same organization, people are producing at roughly the same rate in this study. They didn't work together on the task, but they came from the same organization, and the best organizations, the top organizations, performed 11.1x better than the bottom performing organizations. So Harlan Mills, computer science teacher, actually in my state of Florida in the United States, basically summed up this with, while this productivity differential among programmers is understandable, there's also a 10-to-1 difference in productivity among software organizations. And again, you can see that study. So, what conclusions were drawn from this? Well, we drew that the best performers are clustering in some organizations, right, while the worst performers are clustering in others. Some companies are doing a lot worse than others. And there's something about the environment or the corporate culture that's failing to attract and keep good talent, or making it impossible for good people to work effectively, okay? So 10x engineers aren't really born, they're manufactured, all right? There are practices that are different between these organizations that can make an organization more productive than another, all right? And we're gonna look at some of that. Look at some of this data. I'm not supposed to walk past here, but I'm used to being able to walk all over the place. But let's see. Look at some of this data here. This is the top performing teams here. And look at how they answered some of these questions versus the bottom performing ones. How much workspace do you have? All right, 78 square feet in the top performing organizations versus 46 in the lower performing organizations. Is it reasonably quiet? Top performers, 57% said yes, only 29% said yes in the lowest performing organizations. Is it private? 62% said yes versus 19% in the lowest performers. Can you silence your phone? This was even a big deal back in the 80s, the big chunky conference phones, but could you turn them off? 52% said yes, 10% in the lower performing teams said yes here. Can you divert your call? 76% said yes in the top performing, and do people often interrupt you needlessly? Only 30% in the top performers said yes, 76% in the lower performers said yes. So sorry, Slack, it's not making us more productive. But what this really means, what does this data tell us? Right? They hadn't coined the term yet, but at the end of the day, increased productivity just came down to developer experience. If we produce a better developer experience, then our developers are happier. And if they're happier, they're more productive, right? This matters even more now than it did back in the 80s. Some of you may have seen this statistic. I'm waiting for IDC to push their next report so that I can update this slide. They haven't produced a new report for 2023 yet. But this is staggering, all right? They predicted that by 2022, 65% of the global GDP, 65% would be digitized. And guess what? That prediction came through, and that was only a year ago, right? So now it's gone even more. Now, COVID accelerated this a little bit, but bottom line, that is a lot of code, all right, and a lot of developers. And productivity bottlenecks can be felt at scale now, globally. All right, so this is a very big deal, holding up a large portion of the global economy, right? This workforce, us, right? We are arguably the most important workforce on the planet now because we're holding up so many other industries. Some of you might have even seen that, you know, was it June, I think, last year, that the remaining of the human genome, the 8% remaining of the human genome was fully mapped and turned into a digital twin, which means that we can now run simulations on almost every known protein in the human body, which means we may have the possibility to predict the next emergent pathogen and print a vaccine for it years before it even shows up in the wild. It's amazing, right? And that can't happen without software. Can't happen without biomed and genetics and all that stuff too, but software is essential to it, right? It accelerates the capability. All right, so what does it mean to have a 10x mindset? What does it mean to strive for this level of productivity? What kind of person do you have to be? Well, developers who embody this sort of 10x mindset, and really organizations who embody it, they take ownership of developer experience, right? It's a focus. In 2020, Gartner analysts in the US, they produced, they do this every year, they produce their CEO survey. All right, and it's just, they ask CEOs a bunch of questions. What do you care about? What are you thinking about? In 2020, CEO concern for developer experience was in the single digits. I want to say it was like 7 or 8% or something like that, in terms of CEOs saying, yeah, I care about developer experience. 2 years later, 2022, that figure is over 70%. All right, so in 2 years, C-level concern has gone from really not caring about developer experience at all to caring about it a lot, right? Because the C-suite is realizing how important this workforce is and how sparse it is, right? If you look at that 65% figure, IDC also estimates that we have about a 3 million shortage of developers. We're short about 3 million developers to actually try to hit all of the transformation goals that companies have globally, right? And hiring teams know this now. They know that they have to attract and retain developer talent in order to maintain a competitive edge, right? So this is a concern that was not really a big deal amongst the top brass of a company a couple of years ago, but now it's of concern. So things like IDE tooling, code analysis, acceleration techniques are consistently sought out by organizations who, again, care about productivity this way. But given the state of software right now, this needs to be a company initiative, right? This needs to be something enforced at higher levels in the company. When you look again at some of these organizations that are doing DPE at scale, right? The Netflixes, Twitters, LinkedIn, these folks, they have single teams with hundreds of engineers that are just productivity engineers, right? They serve the rest of the engineers. And if you look at their progression, the microeconomics of this, most of them were DevOps SRE, then they became platform engineers, then they became productivity engineers, right? So it's a pretty clear progression that we can see happening here. Developer productivity is linked to developer experience, and developer experience is linked to mid and C-level company objectives. And developer leaders should seek out ways to improve the experience or build a center of excellence around it. So again, some of these companies who are leaders in this space, they've all built their own developer productivity central organizations, right? So SoundCloud, LinkedIn, Netflix. LinkedIn has over 200 engineers that are just productivity engineers. All they do is focus on productivity, right? So it has to become a company-wide initiative. This also points out, I think, one of the stark differences between something like developer productivity engineering and DevOps, right? In DevOps, what's the ideal DevOps team? It's no team at all. All bots, all automation, right? That's what we want for DevOps. But you can't do that with productivity engineering. You must have empathy for the developer experience, or there won't be a sense of urgency around it. You may make some incremental improvements, maybe make one major improvement, but then it'll regress, right? There won't be the focus, right? You have to have people who deeply understand developer experience who are involved in these teams. Most organizations are not aligned with this way of thinking at all. Anyone familiar with SPACE framework? This is Nicole Forsgren's new productivity framework. Nicole Forsgren is the one who invented Dora. So Dora metrics, if you've heard of that in DevOps before. Google bought Dora from her, and she went off to start another company, and they're focused around SPACE framework. Now, I really like this framework for describing productivity because it's comprehensive, right? It covers all aspects of productivity. Whereas Dora metrics are fine for understanding defect rates and mean time to resolve and all this kind of stuff. It's very focused on the release, right? Very focused on making sure that operationally the software is doing what it's supposed to do. But when Patrick Dubois invented DevOps, he had something much different in mind. It was supposed to be all-encompassing. Developer experience, build code, test on the left here, but also operate, deploy, monitor, right? But that didn't happen at all, right? What really happened in DevOps is that the right side of it, deployment, monitoring, scanning, all that stuff became commoditized with Kubernetes and service mesh and all this great stuff, and very little attention was paid to the left side around developer experience. We thought it was good enough to just, oh, they have nice IDEs, that's all we have to do. SPACE breaks down productivity thinking into 5 different dimensions, right? S for satisfaction. Are you happy doing your job? P for performance. Are you meeting deadlines, right? Are we getting bugs out fast enough? Security vulnerabilities being fixed quickly. Activity. What are you doing? Cranking out code, running builds, all these things. Communication and collaboration, right? How well are team members working well together? Doing things like code reviews, right? Who likes code reviews? Oh, good. That's nice. Yeah, most people don't. But there's very compelling data that shows us, Sonatype actually has this data. If you stop by their booth, I just gave a talk on this at DevNexus last week with a guy named Steve Poole from Sonatype. Some of you may know him. He's one of their lead DevRels. And it turns out that when you really crunch the numbers, the thing that moves the needle the most for security and quality is code reviews, right? Despite all this other stuff, the SAST and Salsa and everything that we're doing right now, code reviews are the ones that actually have the biggest impact, all right? So collaboration, very important here. And then efficiency and flow, which is a lot of what we're going to talk about with developer productivity engineering, right? Productivity engineering focuses a lot on efficiency and satisfaction, right? So this study was actually done by Nicole Forsgren, a guy named Brian Hook, also out who works for Microsoft. And what they did was back in April of last year, so it's just a year ago really that they ran this study, a little less than a year ago. So it's pretty up to date. They surveyed developers, so individual contributors, and then their managers around how they thought about productivity, okay? Now the cool thing about SPACE framework is that it doesn't prescribe to you how to get your metrics, and it doesn't prescribe to you what to do with that data. It's just giving you a picture. So you can gather the data any way you want. So in this study, they just did something very simple. They just surveyed developers and managers, and they asked them, how do you think about productivity? And there's a free-form response, and the way that it works in SPACE is every sentence, if this is a sentence about satisfaction, then it counts towards S. If this is a sentence about activity, then it counts towards A, right? What you really want is balance along all 5 of those things. But look what we have instead, all right? Developers overwhelmingly talked about activity, all right? What am I doing? Cranking out source code, writing code, lines of code, builds, right? Managers thought about performance. They thought about, okay, are we meeting deadlines, right? Are we getting our bugs fixed fast enough? Nobody thought about satisfaction. Wow, okay. And there's really not a balance here at all. So we need to improve productivity for organizations, but managers and practitioners aren't even thinking the same way about productivity, right? We have to align on this thinking. We have to unify. And we need to think more about satisfaction. So let's talk a little bit about the physics of performance. I'm a big fan of what I like to call the ancient business wisdom of the 70s and 80s. I think some of the best processes and new ways of thinking about productivity came out of things like lean manufacturing. And one of those things that would come out, one of my favorite books, I think one of the finest bits of business literature ever written, was a book called The Goal by Ellie Goldratt. Now, anyone read The Goal? What about that one? Anybody? Really? Oh, good. All right, I got 2 great books for you then. So, Dr. Goldratt is a physicist, right? Not a business guy. He was a physicist. But he turned business novelist. His most famous work is called The Theory of Constraints. All right? And even if you've never heard of the theory of constraints, you've heard some of the terminology that's part of this theory. Friction, bottlenecks, value stream management. These are all things that came out of constraints-based thinking. And it's helped form really the foundations of modern business productivity theory still today, right? It is absolutely part of the inspiration that Patrice Dubois had around DevOps, and absolutely the inspiration for lean productivity thinking and all of these things. Still required reading in a lot of MBA programs. And it focuses on treating organizations as complex machines. This is part of the reason that I like this thinking, is that it then says, you know what, we can apply the laws of physics to a business, which is great, because you can't break the laws of physics. So you can come up with very accurate predictions about how a business is going to perform. So it treats organizations as what they are, complex machines. Look, us as individuals are complex machines. Us working together in a corporation, highly complex machinery, okay? But it focuses on eliminating bottlenecks to improve organizational efficiency. That's a lot of it. The Phoenix Project, direct nod to the goal, except for a software organization. The thing about these books, they're not business textbooks. They're fiction. It's a business drama. In the goal, you have a manufacturing company struggling to keep pace with their competitors, and sort of a VP that comes in to try to, fix everything, optimize everything. They send somebody in from the board to teach the VP about the theory of constraints, and the whole book is about this VP applying theory of constraints to the business to help the business improve its competitive edge. So it's a fun read. It's like a page-turning drama. But you're learning. You're learning about the theory of constraints. Same for this book, except it's about a software organization instead of a manufacturing organization. It teaches the relationship between the theory of constraints and DevOps, right? Modern DevOps, right? So both of these, highly recommend these books. So what do these books really focus on? It's about changing our mindset when we think about how a business really performs. Now, traditionally, people tend to look at this type of prioritization. Cost comes over everything. Then throughput, what are we producing, and then finally managing our inventory, all right? The theory of constraints breaks all business process down to these 3 basic elements: cost, the energy and money involved in actually manufacturing something, throughput, money for a business, right? A machine has throughput. What is the throughput for a business? Money, right? And then inventory, the raw materials that are necessary to be assembled at a cost to make money for the business. Now, it focuses on a lot of interesting things. For instance, the longer time you have between inventory becoming a product that you can sell, the slower your throughput, okay? And there's a cost associated with all inventory because of entropy, because of the second law of thermodynamics. Things don't sit still, they rot, all right? That's the very nature of our universe. If I take this laptop and just smash it on the ground, it's gonna break in a bunch of pieces, and it'll be really easy to do that. What about putting it back together? It's very difficult, right? Entropy absolutely guides our universe, and so it guides inventory in a business too. The longer that inventory is sitting on a shelf, it rots, there's a cost associated with it, you have to organize it, you have to keep it up to date, right? And if that inventory is just sitting there, not creating money for the business, throughput, then it's useless. And not just useless, but it's a drag, right? It's a cost. So we have to change our thinking. We have to prioritize throughput, changing our inventory into throughput, and then making sure that we can balance our cost. The biggest fallacy where people just ignore this? Layoffs. And we're seeing a lot of that right now, right? Layoffs are thought of by the C-suite as a way to fix the business, right? Because it costs too much to do what we're trying to do. But if there's no plan to maintain or increase throughput, those layoffs aren't going to work, not in the long run, right? That business will just dwindle, dwindle, dwindle. And we see this play out, right? Lay off 8,000 people. Sure, you're saving some money initially, but then you're suffering with brain drain, rehiring, burnout, right? All these things that come with that. So your throughput goes down, right? So you have to have a plan for both. Yeah, it's great to control costs. It's great, but throughput is more important, right? For the long-term health of that business. So that's the mindset that we have to be in. That's what the theory of constraints teaches us. So if you can just imagine, take a quick stretch. In a software organization, cost is organizational cost. What are we paying our engineers? Inventory is code, okay, right? And then throughput is money. All right. I was developing software back in the late 90s and early 2000s when we would build artifacts on our machines, copy them to hard drives, walk them over to a QA team who would then copy it into their system in a totally probably different environment, and they would test it, break it, inevitably it would get passed back to you, and what's happening here? Inventory, code inventory, with a cost, is not creating throughput yet. All this stuff happening in the meantime while we're testing and building and all these things. And that code rots, right? Because what happens? Security vulnerabilities come out. Oh, we got to stop the release, patch the vulnerability. Oh, there's a new version of this library, but it's got a breaking change. Oh, we can't release it yet, right? So what did DevOps teach us, right? Continuous release, continuous integration, continuous deployment. Always be deploying, right? Amazon was the first model for this, releasing code every 11 seconds to production. Every 11 seconds. Because what does that do? Right? It decreases the time between our code inventory becoming throughput and money for the business, right? So the faster that we can get the source code that the developer is cranking out to a finished artifact that's deployed in production, making money for the business, the better. The tighter we can make that, the better, the less code rot we experience. That's why DevOps has got us doing continuous deployment. It's because of this, right? We want to decrease that window between cost and inventory and then creating throughput for the business. Right? And it's worked very, very well. Right? Big fan of DevOps. Big fan of DevOps and platform and all these other things. So the only initiatives that are positively impacting performance are the ones which increase throughput while simultaneously decreasing cost. Right? This is a hard, fast rule that obeys the laws of physics, and the laws of physics cannot be broken. All right. So, this is our mindset at Gradle. Developer joy equals developer productivity equals business throughput, okay? We do not make a distinction between developer joy, developer happiness, and developer productivity. And I'm going to get a little bit into the neuroscience of that. Okay, look at these kids. Some of us kind of remember how it felt to first learn to code. Some of us feel this way still when we're in our state of creative flow, we're getting things done, right? The feedback that we're getting from our IDE or our build is giving us dopamine hits every feedback cycle, and we're really into what we're doing, right? This is a state called creative flow. And software development is a creative exercise. It's also scientific, though. Super interesting. The brain has been mapped while developers are writing code, and it's this wonderful soup of left brain, right brain activity happening all at once. And you know this if you've written code. You are envisioning the problem that you're trying to solve in your head, and you're coming up with a solution, right? That's creative. But then you do something interesting. You do something scientific. You make a hypothesis with the build tool chain. Hey, I think this code is going to represent the solution to this problem that I have in my head. And now I need you to tell me if I did the right thing. Okay? And when you tell me that I did the right thing, or tell me that I did the wrong thing, as long as that's fast, I'm still in my flow state, right? So these kids, maybe they just did system.out.println hello world, and they hit go, and Java spat out hello world, and they're like, oh yeah, it worked, wow, I did this thing. Or maybe it's Kotlin, and they just did println hello world. But either way, these kids tried something new, experienced an ecstatic state, and got immediate feedback. Now, imagine these kids are waiting 45 seconds, a minute, 10 minutes, an hour, 20 hours in some of the extreme cases that we've seen. The Apache Tika project takes 48 hours to run its full test corpus. 48 hours before you know if you've done the right thing. If these kids are waiting that long for the feedback, they're not gonna look like this, they're gonna look like this. And they're gonna go find some other hobby. And yet we do this to ourselves. We just accept 10-minute build times. We accept hour-long test cycles. We accept test flakiness, because we just love spending the whole afternoon dealing with a flaky test, don't we? Now, that is not happiness. That's not joy. That's not creative flow. That is toil. Toil, all right? What does that word mean? It means work with no engineering value. Toil. And we sure experience a lot of it in this workforce. A guy named Danny Thomas, who's a productivity engineer for Netflix. I interviewed him talking about their practice. You can see it online. It was one of our DevProdEng webinars. I can show you where it is at the end if you want to look at it. He said something to me in that interview that has just etched into my mind, and it's a driving force. He said, "It is staggering the amount of toil and friction and frustration that engineers are willing to put up with." This is something that I think we've convinced ourselves is an occupational hazard of being a developer. This is just what it means. We have to deal with these types of frustrations. But here's the thing, we don't. If we actually start focusing on these problems and applying process and technology, we can really improve things. And at the end of the day, that's what developer productivity engineering is all about. Focusing on the tool chain, looking for bottlenecks in the tool chain, looking for slowdowns in the technology, the tools that the developers are using, right? It's not focusing on people. There's nothing wrong with people management, but that's not what this is, right? We're not looking for new behaviors from people. We're looking for better behaviors for the tool chain that those people are using, right? And we're not talking about Kubernetes, better deployment, right? We're talking about local, build local development, right? The developer right there at their workstation. How can we make that experience better? Nope, saw that already. So, if the best code is written by happy developers, we should strive to foster developer joy. Because again, software innovations are augmenting global innovation and solving some of our biggest challenges. But instead, enterprise software development is causing a whole new unique set of frustrations. There's this irony in play, especially in the enterprise, that as a software project becomes more successful, it becomes worse to work on, right? Success of the project, developer experience goes down. Why? Increasing lines of code, increasing dependencies, increasing the number of tests that we have to run, increasing the number of other developers that we have to coordinate with and not have merge conflicts with and all that sort of stuff, right? So we have this interesting irony that as our software projects start making more money, more throughput for the business, the experience of working on those projects becomes worse and worse and worse and worse and worse. Regression, regression, regression. This is the pattern that we need to get out of, okay? Developers start their day coding. Yay, we're in our creative flow. We're great. We're happy. We're doing what we want to do. And then we're waiting for the build to complete. And then it fails. So we're just going to spend the rest of the afternoon trying to debug some build failure, probably with inefficient tools and not enough data and visibility into the problem because maybe it built in some ephemeral CI environment that destroyed itself 30 seconds later, and the console log is gone, and we have to try to recreate the problem or who knows what, right? It's not that if the build goes red that we're out of our flow state. It's just a new problem to solve. But if we're spending an hour trying to diagnose this problem, no, we're not in flow. We're experiencing friction and toil. Okay, so debug the build failure, go lunch, play some ping pong, whatever. Coding, we're back, we're good. On our local build, we gotta wait on it, but it works this time, great. So now we're gonna pass it to CI and we're gonna wait again for the CI build to complete, and then tests are flaky. Tests that we're succeeding in our local environment are failing in CI, so we're gonna spend the rest of the day having a great time investigating some flaky tests. We can do so much better than this, and we need to. We need to cut our average build times. We need to decrease build and test failure time to resolution. We need to get 100% visibility into the data that we need to reduce build, test, platform, and CI failures. So this is where developer productivity engineering comes in. It's a new software development discipline that uses acceleration technologies to speed up the software build and test process and data analytics to make troubleshooting more efficient. And the aim here is to achieve faster feedback cycles, more reliable and actionable data, and then a highly satisfying developer experience. And that is at the core of all of this, is developer experience. All right, so let's be very clear about the different problems that we're going to be solving with DPE. If you can imagine that this is a developer, and this developer is surrounded by feedback cycles, right? The basic quantified unit of developer experience, the feedback cycle, right? The thing that's really going to determine whether we're having a good time and in our state of creative flow, or whether we're miserable and experiencing friction. So these are feedback cycles, and this could be in a local environment, or a remote environment, or CI, right? But sometimes things are fine. Sometimes they're slow. And we've talked about that a little bit. Sometimes they're too slow. Builds take too long, test cycle times. Sometimes they're too slow to fix. Again, we said this before, build goes red, you're not necessarily out of your flow state, but if 45 minutes later you don't have the data you need to solve the problem, you're not feeling very good. And then finally, this is the worst one right here, the worst one. The problem that could have been avoided altogether if we had just been a little bit more proactive with our analytics. Again, things like flaky tests, avoidable failures, right? Things that if we were proactively aggregating this data, but nobody is, but if we were, we could be dealing with. You know, if you have an hour to improve your build, shouldn't lean on that. If you have an hour to improve your build, where do you spend your time? Right now, that's a hard question to answer. Anecdotally, we have to rely on our developers to say, oh, I have the worst problem in the world, but you don't know that without data, right? So proactively using data to eliminate problems so that developers never run into them in the first place, because everything is infinitely more than zero. So you can think of it as sort of a continuous improvement flow, but the outcomes of these are faster and more consistent feedback cycles, a more reliable and consistent tool chain, and a better developer experience. This reliability and consistency is really important too. You know, if we fix the build, oh, it's 10 seconds, great. But every now and then it's an hour. Developers are basically going to think, okay, this could take an hour, so I'm going to cram in a bunch of code because I just don't know, right? So we need consistency, right? And this really is the next big thing in software productivity. We are seeing this bear out. And when we say that it's the next big thing, like we mean this very, very literally. We're chasing bottlenecks, right? So these are some of the practices that came out of things like the theory of constraints, again, the ancient business wisdom of the 70s and 80s, just-in-time manufacturing, business process reengineering, and change management. But then when software ate the world, these productivity practices became more focused on software organizations. So we had like Agile, Lean Six Sigma. This would give way to DevOps. But what are we doing? We're just chasing bottlenecks. Again, we're just eliminating the bottlenecks to throughput in the organization. What's causing the code to not get out to production fast enough to make money for the business? So DevOps has achieved great things, mostly on the right side of the continuum. But we do have like instant releases. We do have A/B releases. We have canary testing. We've got wonderful service mesh that can, you know, show a new change to 0.5% of our users. We have semantic versioning that can allow us to pull patch releases automatically. We're starting to get great supply chain security and things like this. Great. Now we have a new set of primary bottlenecks, right? The new set of primary bottlenecks are right there in the local developer experience. That's why we say DPE is the next big thing. We're just chasing the primary bottlenecks. And we've had this interesting mid-step in platform engineering, which if you're interested in productivity, I highly recommend you look into platform engineering as well. DPE can optimize a platform engineering team. So it affects developer happiness. Most developers want to work in an environment that enables them to work at their full potential. And we could get rid of developers and just say workers there. You know, nobody really wants to show up to fail, right? Organizations that can't provide this environment are going to lose talent, right? The coding war games totally bears that out. But software is so much more selective now, and we do so much more with it. All of us have way more options for employment than we used to have, even just a few years ago, right? So organizations that aren't able to provide a good developer experience will lose talent, which means that you'll lose your competitive edge and your throughput will diminish. We need a culture where the whole organization commits to this effort. And you need a team of experts whose sole focus is optimizing the effectiveness of the developer tool chain. Again, this really underscores a difference between DPE and DevOps, right? DevOps, all automation. DPE is people, right? Practice and our priorities and success criteria is primarily based on data that comes from a fully instrumented tool chain, right? We're not guessing, right? We can actually see, oh, we took the builds from 10 minutes down to 30 seconds, and that's consistent. Right now, most organizations have no idea what a local build looks like for a developer. I ask this question to all types of crowds. I'll ask it again in this workshop. I asked it last week at Dev Nexus. I asked it the week before that, Salt Lake City DevOps Days, about 300 people there. Java Land, back in Cologne, Germany, just a month ago or so, whenever that was. Same thing, maybe I had 50 people in the room. Ask very simple question. Who is tracking local build times for developers? One person. That's pretty typical. Yeah, maybe one person. Yeah. And good, I'm glad you're doing that. Everybody needs to be doing this. If you come away with one thing, one tidbit from this whole workshop, one actionable thing, set up a way to do this. It's not hard. All right, look at your build tool chain, whatever build tool you're using. Most of them already have some plugin or module or extension you can load to get this information and export it some way. And if not, you can build your own plugin. I mean, most of these build tools are open source, right? And build a simple build plugin that just says, okay, take the amount of time that it took to do the build, stick it in a Prometheus database somewhere. Make it visible, right? Because once you do that, that's gonna set up all the rest of your productivity initiatives. You're gonna look at this and you're gonna be like, this is terrible. I can't believe that our developers are putting up with this. And you're not gonna be able to unsee the problem, okay? So it's a great first step. We surveyed a bunch of people who are doing DPE at scale. No surprises here, 81% agreed that DPE made their job more enjoyable. All right, and the other 19%, it wasn't like, oh no, that's not true at all. They were like, oh, I don't really know. I don't know what DPE is. So pretty promising here. All right, so that's a lot of the theory and the appeal. Let's actually start breaking this down. The rest of this workshop is going to kind of be organized into sort of 5 sections. We're going to look at the 5 distinct pain points that developer productivity engineering addresses. We're going to break them down, and then we're going to look at the process and technology and outcomes that we can expect by applying DPE practices to try to fix those problems. Okay, so that's kind of how we'll format things. These 5 major pain points, what are they? We've already talked about the first one ad nauseum, right? I think we all can agree here. Waiting for builds and tests to complete is one pain. Inefficient debugging, we kind of talked about that too, right? Again, you know, a red build is not going to take you out of a flow state, but having no data and no visibility into the problem you're trying to solve definitely will. Flaky tests and other avoidable failures. Flaky tests. Spotify has a whole paper on these where they call flaky tests the infinite pit of sorrow for developers, and I think that's pretty apt, right? They decrease trust in the tool chain. They're expensive and difficult to diagnose, and they sometimes, let's be honest, a lot of us just ignore it. Like, oh, the test failed, run it again. Oh, it went green, great, done. No metrics or KPI observability. Again, nobody's tracking local build times. And even if you do improve the build once, how do you know it's going to stay that way, right? You could update a new version of an annotation processor or endpoint security, something like that. All of a sudden, the build slows down. Nobody knows. Usually goes unreported. These things tend to happen slowly. Oh, this little thing added 10 seconds. This little thing added 20 seconds. This little thing added 5 seconds. And then before you know it, the build's slow again. Okay? And then all of this does improve CI. Now, you can make the argument that there are elements of CI that impact developer productivity. A bit, yeah. But I wouldn't really call this so much of a productivity thing, but it bears mentioning, right? Because we've definitely had CI engineers who the outcome that they see from DPE is agents aren't queuing as long, not as many builds are being run because developers aren't running builds 10 times in a row because they're failing, right? And so it reduces their ticket load, right? We just made a pretty significant donation of our software to the Apache Software Foundation, which is great. They'll have about 400 top-level Apache projects that are capable of now using this DPE platform. But the 2 people that are sponsoring this initiative and are most excited about it are the CI infrastructure team. Because imagine what that must be like to run the one CI for 400 top-level Apache open source projects with anonymous committers and PRs happening all the time. All they do is field tickets, right? And they are super looking forward to things like developer self-service troubleshooting so that they don't have to spend 5 minutes to go scrape some Kubernetes console to tell somebody that they were just building against the wrong JDK or something like that, right? Now developers can glean this on their own. Okay. So pain point number 1, waiting for builds and tests to complete. This is the pain. This is the benefit or outcome. And we want to use build acceleration technologies to achieve this. Okay. So fast feedback cycles are important, right? We've talked about this a bunch. Let's break it down. There are some obvious new impacts to improving cycle times, and I would say some less obvious ones, right? Faster feedback cycles, well, less idle and wait time. Well, what does that really lead to? Less context switching, less changing focus from one thing to another while we're waiting on a build to complete. Because we do that. If we know we have 15 minutes, 20 minutes for a build to run or test cycle to run, we're not going to just sit there twiddling our thumbs, right? We're going to go do something else. Maybe check email, Slack, whatever. But there's a cost associated with that, and it's called a context switch. Now, we know from neuroscience that it takes anywhere from 10 to 12 minutes for the average human to be able to adequately shift their focus from one task to another, right? Over the last decade, very compelling research has shown us that we really can't multitask, right? We convince ourselves that we can, but we can't, right? But what's even worse, what we found over the last couple of years, is that it's actually bad for our executive functioning to try to force ourselves to do this. Every time you context switch, it increases the amount of glutamate in your prefrontal cortex, which has a direct impact on cognitive fatigue and stress, right? And cognitive fatigue is slippery, right? The reason it's slippery is because it's hard to see. Developers can basically do their jobs. You do your task, get stuff done, you drink your coffee, Red Bull, whatever it is, but get the work done. But you don't have the energy to elevate your work. It's hard to innovate. It's hard to think about the next big step when you're cognitively fatigued. And so business innovation is directly impacted by the amount of context switching that developers are doing. It's just neuroscience, right? So what does that lead to? More focused developers, better quality, and better productivity. All right. Well, there are some less obvious things that happen here too. When feedback cycles are faster, developers tend to build more often, right? Which means that they're asking for feedback more often, which means they're refining their work more often, which leads to earlier quality checks, fewer expensive downstream incidents, ultimately better quality, faster mean time to resolve. And then we tend to put in smaller change sets, right? If we know that we only have 5, 10 seconds to wait before our build's complete, we can make small incremental changes, right? And find our quality checks earlier instead of cramming in a whole bunch of code all at once because we know we have to wait an hour, which is going to be a larger change set leading to merge conflicts and less efficient troubleshooting, all right? So all of these cascading impacts just stem from improving feedback cycle times. It's really amazing, actually, all these new behaviors and effects that we can get by focusing on this. So I like this quote about flow state. I think a lot of us can sort of relate to this. It's being completely involved in an activity for its own sake, and the ego falls away. Time flies. Every action, movement, and thought follows inevitably from the previous one, like playing jazz. Your whole being is involved, and you're using your skills to the utmost, all right? And what does this do? It makes us happy, right? Cal Newport, talking about deep work. He talks about this as the definition of deep work as professional activity performed in a state of distraction-free concentration that to push your cognitive capabilities to their limit. These efforts create new value, improve your skill, and are very hard to replicate. All right? This is what it's all about. It's all about flow state. Quality of creative flow and collaborative effectiveness equals better team productivity. We want to get ourselves out of this. Now, it is both funny and sad that this comic is true, right? It is funny. I think we can all relate to it, but it's also a little bit sad. So this is the mindset that we need to fix. Number one excuse for legitimately slacking off, code's compiling. Okay, fine. Do whatever you're doing. Of course, we could also say this about testing, right? Which we know that on average, enterprise applications spend like 90% of their cycle times actually running tests. Bears out for a lot of like open source projects too. Kafka, for instance, I want to say has like 24,000 tests that it runs on its build, right? Spending the majority of the time running tests. So that's a lot of what we're focusing on too, not just accelerating the build, but also accelerating the test cycles. I have a sinking feeling that we might be getting here A little bit concerning. I think we're all going to be prompt engineers in like 5 years. Let's put some math behind this. All right, these are real numbers that came from running trials against our own software. Look at what's happening here. This team of 11 with a 4-minute build time is able to run about 850 builds on average per week. Okay? This team of 6, just a little over half that size, with a 1-minute build, is able to refine their work over 1,000 times a week. So this team of 6 has a higher likelihood of producing higher quality software than this team of 11. A couple of takeaways here. First of all, nobody's complaining about a 4-minute build. And that's a big part of the problem, because you should. 4 minutes is toxic. You can't context switch at all in 4 minutes. What are you going to do? Nothing. Just a waste of time. Okay? So taking a 4-minute build down to a 1-minute build can have a really significant impact on the work that's being done by your team. But there's even more interesting math here. Look at what happens when we brought this build time from 1 minute down to 0.6 minutes. Again, nobody's complaining about this. But what happens when we fix it? At 1,000 builds a week, we're returning 44 engineering days a year back to this small team of 6. It's almost 2 full vacation cycles, right? What about this large team? 12,000 builds a week with 100 devs at a 9-minute build that we took down to 5 minutes, returned 5,200 days of engineering value back to that team in the year. Amazing. So the faster the build, the more you stay focused. As build time increases, people switch more and more to do different tasks, and that cost of context switching has to be paid. Whenever work on the previous task has to be continued after the build finishes, whenever the build fails, whenever the build was necessary to provide some sort of immediate feedback. And we know, again, that this context switch has a tax, 10 to 12 minutes, really. And it has to be paid twice. New task, and then fix build a previous task and start a new build, go back to the new task, all right? So that's like 2 context switch just to run a single build. And an unreliable tool chain is going to significantly increase this cost. When local builds take longer, that change set of a single push is increased. The bigger the change set, the longer it's going to take on average to debug a failure, right? If we made a 1-line change and it broke the build, you can pretty much blame that 1 line. If we added 100 lines of code, it's going to take a little longer to diagnose what we might have broken. When CI builds take longer, the number of contributors with changes per CI build increases. Like for the master build, for instance, and debugging a failure is often significantly harder. Again, because that build is happening in a different environment. And nowadays, those environments tend to be ephemeral or running on cloud, something like that. The pull request build takes longer, which increases the likelihood of merge conflicts, right? All right, so that's a lot of theory. But let's start talking about technology, all right? What do we actually have available to us that can fix these problems? Well, we have 3 distinct acceleration technologies that we're going to talk about. And the first one is build caching. Anybody heard of a build cache? All right. So, first off, this is not a dependency cache. All right, so if you're thinking, oh, well, we set up Artifactory and it was great, we already did that. No, that's not what we're talking about. We're talking about a build cache. All right, we're talking about a cache that can actually take the output of individual steps of an artifact build and pull that output from cache as opposed to having to run that part of the build again. It was introduced to the Java world by Gradle in 2017. It certainly exists in other build frameworks. Clang has a build cache. Bazel has a build cache. Maven just released an open source build cache that we've been providing one from Gradle Enterprise for a long time, but they released an open source one back in generally available in October or November, something like that. So the takeaway here is go look for one, right, if it's not already turned on. By the way, if you're using Gradle, it's not turned on by default, right? You actually have to go into Gradle.properties and switch it on. So seek these out. And again, just to clear up any ambiguity, just know that these are not dependency caches. They're complementary to one another, but they're not the same thing, right? I know I repeat that a lot, but I've been in conversations, like hour-long conversations with prospects and things where I hammer on this, and then they're like, 50 minutes in, they're like, oh, sounds really good, but we already tried this with Sonatype Nexus, and it didn't do anything. It's like, no, it's not what we're talking about. So just make sure that you take that away. How does this work? Well, in the case of the Gradle Enterprise cache, inputs are going to get passed into Gradle tasks or Maven goals or Bazel targets or SBT actions. What are those inputs? Well, like source code, JVM major version, that kind of thing. And we're going to derive a key from that. And then whatever the output from that task is, whether it's a set of compiled class files, a JUnit XML out, whatever it is, we're going to stick that in the cache against the key. All right, so that if we ever encounter this exact same scenario again, and it is very sensitive, but if we ever encounter this exact same scenario again, then we will not run that scenario. We will just pull the output from cache. And because this is key-based, we can distribute this, right? So we could actually have like a remote follow-the-sun type of team populating a cache or a remote cache overnight that you can then benefit from first thing in the morning. So a lot of us might be used to pulling down all the changes from the offshore team overnight, and then we hit go, and then we wait an hour, go get coffee or whatever, right? You don't have to do that anymore. Your first clean build of the day using a remote cache can benefit from what's been populated in that cache. Okay, but it is also very sensitive because of this, right? So if you're, for instance, generating timestamps as part of a task, well, those timestamps are not going to match, so your input's going to change, so you won't be able to pull from cache. Our solutions engineers, this is probably where they spend most of their time with our customers, is optimizing builds for cache. But it is generic, so it can apply to a lot of different tasks, not just build and build compile and stuff like that, test compile, running the test, right? Anything that has a standard set of inputs and outputs can be introduced to the cache, right? Sometimes you have to go in and do weird stuff, like you might have a task that's not producing any output, so you like give it some fake output to put in the cache just so that it can actually pull something, right? But in general, as long as you have standard inputs, standard outputs, you probably are going to be able to have a cacheable task. So describing the behavior of this cache a little bit and some of the benefits, let's pretend that we've got a project with 4 modules, because caching is, as you can imagine, most effective for multi-module builds. We've got these 4 modules: core, service, web app, export API. If it's in Gradle, then it would be called out this way, but just know that this is what we've got. And then understand the dependency flow here. So export API depends on core. Nothing depends on export API. Service depends on core, and web app depends on service, but nothing depends on web app. Okay, so that's kind of what the hypothetical application that we're sort of setting up here. Now, in general, when we're making any change at all to a Maven project, or we're running a clean Gradle build, all of these tasks would have to execute under normal circumstances every single time we made a change and wanted to run the build again. Okay, but if we're caching, things change a little bit. What happens if we change a public method in export API? All right, well, we have to recompile our test, and we have to recompile our code, and we have to run our test and run our check style, but nothing depends on export API. So all of these tasks could be pulled from cache. Okay. What about this? A little bit more invasive, changing a public method in the service module. Well, we do have to compile our service module and our test and run our test and do check style. And our dependent module, because it was a public method, we will have to recompile it and recompile its test and run its test again. But we won't have to check style it because we didn't change any code here. And all of this stuff can get pulled from cache. Okay. What about changing an implementation detail of a method in the service module? So not changing the public method, but just an implementation detail. Well, in that case, we have to compile the code. We don't have to recompile the test because we didn't change the public method, but we do have to run it. We do have to check style it because we changed the code here. And we have to run this test again, but we don't have to recompile the test or run check style or recompile any of this. And all of this can get pulled from cache as well, right? Starting to see some of the benefits here. And what about an implementation detail of the core module? Well, we have to run all of our tests and recompile our core module and recompile our check style, but it was an implementation detail, so we don't have to reperform any of these tasks, even though this was kind of invasive, right? We changed something that everything basically depends on, right? And then even like the most invasive change that we could make here, where we've made a change to the core module, a public method in the core module, we have to do a lot. We'll have to recompile this, compile everything that depends on it, compile all the tests and run them. But at the very least, we could pull the check style tasks from cache, right? So there's still some benefit here, even with the most invasive change that we could make. So even with only a few modules, a cache can significantly reduce build and test size. For larger multi-module builds, sometimes 50% of these modules are considered leaf modules, right? And so the last build time is reduced then by, indirect proportion n, with the n being the number of modules. So checking the inputs and downloading and unpacking items from cache does introduce some overhead, but usually that overhead is nothing compared to the actual benefits that you get. But you should be monitoring that, right? We have had circumstances where people are pulling from remote caches and the network fabric is bad, or it's in an availability zone that has too much of a network distance, and so it's actually deleterious to the build time to be pulling from cache because the overhead of the network bandwidth takes more than running that actual task would have taken, right? So you want to keep an eye on this to make sure that it's staying effective, but in general, that overhead's going to be negligible compared to the benefit that you're getting in terms of the build speed. And then to make this work, though, really well, the inputs do need to be stable and portable, so there are some common problems that can cause cache misses that you can generally fix, right? Things like generated timestamps from source code is probably one of the biggest ones, especially like dot properties files and stuff that we're dropping, so like a git.properties, or if you're doing like a build info plugin and like build info.properties, that generally is going to have timestamps in it. So absolute file paths, so sometimes there's going to be references where accidentally, instead of saying like, curly bracket program directory, instead you're actually like /user/home or to derive it from your own environment variable. When that actually gets in, your home folder is going to have a different name than some other user's home folder, so you could introduce a cache miss there. Non-deterministic ordering of the build can cause problems here as well. But yeah, I mean, on average, we're looking at, with Maven projects, the Maven multi-module projects tend to have a huge input. We average around an 86% time saving per build on build cache with Maven. So it just uses a local, like a cache directory that's just sitting there on your local machine. But there is a remote one as well, and it can speed up development for a single developer or a build agent. So again, CI can benefit from caching as well. And it reuses the build results when switching branches locally. So let's look at a demo. I'm going to try. I was having issues with the display earlier where it wasn't mirroring. So I'm hoping that it's going to mirror. Yes. Okay. So let's take a look. So here we've got, and I'll show you a Gradle version of this and a Maven version of this. Just a very simple app. It's not doing very much, but we do have the caching turned on. So this is how you switch that on for Gradle. And we're just going to run our first example here. I'm going to remove the current build cache just so that we don't pull from that. And we're just going to run a clean build. Oh, wonderful. I know what's going on here. Well, let me run a different example here. I actually like this demo a little bit better anyway. So this is a Maven build instead that we're doing, and just a simple Maven build that we're going to run against a event server that I have set up here. All right. So we'll do a clean build first. Oh my gosh. I'm just having total demo karma here. Oh, thank you. Sorry, everybody. something, it's not able to hit my, it's not able to hit my event server. All right, well, we should still be able to see cache benefit here, though. Yeah, I don't want to waste too much time here. The problem is that I'm having issues hitting my external server, which enables me to actually use a cache remotely. Let me just double check a couple of other things, but I think we may just skip this one. You can kind of get the idea anyway. See, this is it right here. All right, well, I apologize. It's a network issue, but we can, if you want to see a demo of this, like I'm going to point you to, at the end of this, an activity that you can do on your own called our Build Speed Challenge, where you can actually hook one of your own builds or an open source project or something like that up to a test server. And if you do it and send us a screenshot, we'll send you some nice swag, sticker, mug, socks, and that kind of thing anyway. So I'll make sure that you have that as a leave behind, and of course you can come by the booth, but yeah, I apologize. And we may have some issues with the other demos here if I keep running into this network issue. There's weird ports being blocked, and it's on the speaker network, right? Yeah, I'm on the speaker network, so strange. Anyway, sorry. But let's move on. Okay. What you would have seen is, hey, the build took 15 seconds, and then it took like a second because we skipped a whole bunch of tasks because it read stuff from cache. All right, remote build cache node I mentioned is a good architecture as well because this allows remote teams to populate the cache. So in this case, we would have developers actually checking code into CI like maybe overnight, right, offshore team like that. And the CI is running the builds and actually populating this remote cache that you can then pull from locally, right? So again, great for follow the sun teams, also great for ephemeral CI environments, right? Because we said before that the local build cache is sitting in a local directory, but what happens if that environment's getting blown away every single time it runs its test set, right? Well, the cache is going to disappear too. But if you have a remote cache, then you can actually set up ephemeral CI nodes that can read from the cache as well. All right. So we will try. I do have at least a local instance of Jenkins running. So we may be able to see the cache benefits just running this build locally. Let's see what happens. Oh, excellent. Okay. So here it's working. But this is because this isn't relying on anything external. So this is actually that same demo project that I was hoping to show earlier, but running inside of my Jenkins environment instead against a remote cache node. And it's just a Spring Boot app. But what I like about this as a demo is that it is a full life cycle, right? There's compile, there's check style, there's actually running unit tests against it, which is what it's doing right now. Oh, boy. Now it's complaining about the network again here, though. Oh, okay, but it worked. Great. So 44-second build in this case. And we can go take a quick look at what's called the build scan, which we're going to be diving into later. And see how this performed cache-wise. Well, here's the build cache details. Obviously, there was nothing in the cache, right? We blew it away, so they were all cache misses. But we should have stored three tasks in the local cache and 3 tasks in the remote cache. Okay, great. So then let's go run this build again. And normally I'd be running it in my IDE, but I just don't trust that right now. So let's run this build a second time. And look at that, 3 seconds. 3-second build. We loaded 3 of our more expensive tasks from cache, saving at least 32 seconds, which it knows from keeping track of the build time history, right? So it's able to calculate an average build time because it was keeping track of that, right? So yeah, safe to say, it's pretty good savings there. Now, I mean, will you have made legitimate changes? Will it always go this way? No, of course not, right? When you make legitimate changes to the code like we saw in the scenarios earlier, there are tasks that will have to be rerun, but you can pretty much always save some stuff, and the more modular your application is, the more savings you should expect, right? Great. Not a total demo failure. And I'll see when we take a break, which we will do. We may as well take it right at the 90 minutes, and we'll do like a 10-minute break. I'm going to mess around with my network settings and see if I can get any of this stuff working a little bit better. Okay. So that's our first acceleration recommendation, is build caching. And again, depending on your tool chain, what build tools you're using, that may look different, but seek it out. Right? See what's available for you. Most of the major build systems have something like this that'll work. So, second thing, test distribution. So we mentioned that a lot of the cycle time is spent waiting for tests to resolve. In many cases, 90% of the overall build is happening in tests. In the demo that we just saw, most of that 44 seconds was spent running those tests in the middle. It took a little longer because we were having the slow hostname resolution, but you get the point. So let's focus on accelerating tests. So build caching is great when we haven't made legitimate changes where we actually have to rerun tests, right? But what about when we do make legitimate changes where we have to rerun tests? Well, we should try to run those tests in parallel as much as possible. We've seen existing solutions for this, like for instance, if you're familiar with Gradle, you might know about the -- parallel flag, which allows us to control project parallelism. We can also set a max number of workers that we want to put on this, max parallel forks, but which is great, but you're limited to the resources on your machine. CI fan out. This is a popular one. I mean, you can kind of understand why. You build a pattern here where you're manually partitioning sets of tests like this, and then you're creating a parallel pipeline in which those tests are going to execute. Okay, so yeah, we've achieved some parallelism. But what we really recommend is a pattern that looks more like this. Now, you can replace this with just scheduler, right? Just a test scheduler. But what does our architecture look like for any local builds or CI builds? We have test distribution agents, in our case, that are running as single Docker pods in Kubernetes with a KEDA, Elastic Horizontal Pod Autoscaler, associated with that pod. So we're letting Kubernetes do most of the lift for us in terms of elastic scale. But these agents are effectively being fed tests from the build system and being scheduled directly from the build tool, right? So this helps in a few ways opposed to some of these other features, right? So build caching, great, but in many cases doesn't help when test inputs have legitimately changed, right? Single machine parallelism, limited by the resources that are available to us by that single machine. And then CI fan out, a whole bunch of problems, right? It doesn't help during local development. Again, build local. It's inefficient, in particular on ephemeral CI agents. It requires manual setup. You have to partition the tests yourselves. And then it means that you also have to figure out how to collect the results of those tests by yourself too, right? But if you had actually scheduled this directly from the build tool, all of that stuff would be coming back to you as if you were just running a normal build, and it would also work locally. Great example here. And again, my friend and colleague Danny Thomas is kind of featured in this article. You can see how Netflix used just 2 of these technologies, build cache and their own test distribution setup, to take a 62-minute test cycle time on one of their backend Java APIs down to under 5 minutes, right? Which has fundamentally changed the way that team is able to work on that project. Right. I'll give you a minute to... I think that's everybody. Okay. Oh, sorry. Do you want to go for it? I will figure that out too. Yeah, I'm not exactly sure. This is my first Devoxx, so I'm not sure how they handle it, but I'll try to figure that out. If not, you'll have my email address, LinkedIn, whatever. Feel free to reach out. I love talking about this stuff. And oftentimes, people learn about this and like, oh, I wish that I could, you could come talk to my team or whatever. Like, I can. I'm very happy to do like Zoom lunch and learns, any of that stuff, right? It is my job to spread this to the masses. So yeah, we can always figure out some kind of follow-up that way. All right, so we talked about build caching. We talked about test distribution. The third sort of acceleration leg, if you will, here, involves machine learning, right, which is going to take us to even better efficiencies around testing. This type of stuff is kind of predicted. Again, you notice Gartner, I'm a big fan of the business analyst group. Look at where they have said the AI use case for software development and testing sits, right? There's a lot of this, but we're focused on test set optimization and then optimal test selection here. These two things are what we're going to focus on for this bit of the acceleration technology. And we're going to focus on a relatively new technique called predictive test selection. Sorry about that. So my hair dryer this morning blew a fuse like midway. I'm not used to going around with wet hair, so sorry about that. Predictive test selection. Anybody heard of this? It's pretty new. All right, nice. Nice, all right. So we didn't invent this. Facebook and Google invented it. Facebook pushed this paper back in 2019 talking about predictive test selection. But this is effectively, it's a new approach to test impact analysis, right? So traditional test impact analysis, we look at a dependency flow, right? Like, okay, you changed this bit of source code, which could impact this test from a coverage perspective. So JCoco or whatever is going to say, hey, you got to run these tests because you got to improve your coverage from these things you changed here, right? Fine. But the problem is, a lot of times, those tests are just going to succeed. Feels good, but every test that you sit there and watch succeed is a total waste of time if you think about it, right? Test failures are useful, right? That lets us know that something broke, right? We should address it. A test succeeding, it's a waste of time. You spend Kafka, run 24,000 tests in Kafka, wait an hour for them to complete, they all succeed. You might pat yourself on the back, yay, but as a waste of time, right? It would be better if you could have just known ahead of time that those tests were just going to succeed, which is exactly what predictive test selection tries to do. We use a predictive model. In the case of the Facebook implementation, a learning model based on XGBoost, which is a gradient-boosted decision tree method of machine learning that's not deep learning, so it doesn't require a GPU or anything like that. It works on just a normal processor. But we want to evaluate the usefulness of tests in a certain test set. And then we really only want to run tests that have a likelihood of providing valuable feedback. Okay? So if the test isn't going to, if it's just going to succeed, then don't bother running it. When we can do this, test cycle times can be significantly reduced. This is one example. Which one is this? Yeah. This is the open source detect application. And you can see that right here, what they're considering their savings potential. In other words, if we turned on test distribution, we would have been able to avoid 75,000 tests in the last week, saving a cumulative serial 2 days and 11 hours of collective time. Now, that's not wall clock time, right? But still, being able to basically carve out 2.5 days worth of wait time in a week, it's pretty good. So conventional test selection kind of works like this, right? These red areas are source code files that have changed, and because we've got this this graph that links, these two source code files to, number one, these are tests, number one, number two, number three, number four. These are the tests that we're going to select kind of blindly, just because we know, you might have messed something up, and so maybe you should run the test and see if you did. Right? This is kind of how we do test impact analysis or conventional test selection today. And in our typical feedback loops, like a single change, run some tests, run pretty often, and local pre-commit checks, so just incremental stuff that we're doing on our laptop, or pre-merge CI jobs, right? So stuff that we're running in the outer loop but before we've actually merged and deployed, this is where we recommend turning on predicted test selection. Post-merge, run all your tests, right? We, this takes some getting used to, right? Especially if you've been doing this for a long time, where you're like, oh, skip tests, I'm not gonna do that, right? Pre-merge, post-merge, run your whole test set, right? But you can still save yourself a ton of time incrementally, locally, when you're using a method like this. So what does this approach look like? It's very different. When we make our changes, we then generate based on a history of changes that we've learned from in the past. When we create features about like, a source code file change or an extension or things that have just been failing a lot recently, right? There are all types of different features that we use to actually train the model, and they're all laid out in that white paper, right? Everything you need, the whole blueprints for creating your own predicted test selection model are laid out in that white paper. Soup to nuts, you can do it all. We look at the history of changes and we generate a score. How likely is this test to fail given the set of circumstances and the history that we've learned from? And then under a certain threshold, we don't run the tests that have a low probability of failing, right? This is telling us that tests 5 and 6 have a high probability of failing based on the changes that went in, so we're gonna run these. But these all have a very low probability of failing, so we're not gonna run them, right? So that's effectively how the model works. If you're interested in a little bit of how the model is trained, and again, this is all in the Facebook paper as well, you can kind of see some of the features here that are like interesting. Like file cardinality, for instance. This ranks fairly high in terms of feature performance for helping us determine whether something's going to fail. But like number of tests, the number of tests that are actually run against it, think about that for a minute. If I have to create like 50 tests for a single function, there's a pretty high likelihood that that single function is problematic. Like, why else would I have to create so many tests to look at it, right? So the larger test set is going to increase likelihood of failure. File extensions, interestingly, have had some impact. Change history for files as well, right? So these are some of the features that are used in the classifier to train the gradient boost model. Some of the features of the changes that are actually looked at to learn from and then make this determination later. But effectively what's going to happen is when a test run starts, the build tool is going to submit a snapshot of all the tests that it thinks that it needs to run into the model. And then the model is going to look at that, and it's going to look at these different features like file extensions, number of affected files, some of these things that we saw, project name even, historical failure rates. All of these different features are used to train the model, and then the model is going to generate this probability of failure, right? So getting back to that picture, right? So this probability of test failure is what's going to come out of this model based on all those features that it's observing. And again, we've seen a lot of effectiveness here. The Micronaut Foundation has been using this to a lot of advantage. This is in a 1-month period, saved 46 days of serial execution time with a 70-day savings potential in that month. Now, Micronaut runs a ton of builds and tests, right? They're running like 100,000 builds a week or something crazy like that, right? So that's where these savings come from, but nevertheless, the math checks out, right? Gradle build tool. We famously overbuild the Gradle build tool. I mean, I think like we build this thing like every 10 seconds or something like that. It's ridiculous. So our savings in this month-long period were 1,607 collective days of serial execution time that we peeled off by turning on predicted test selection, okay? JUnit, also using it. They don't build as often, but in this 1 week period, they saw 15 hours and 7 minutes of total savings potential here by using this. All right, so it can be very, very effective. Now, if you look into the white paper, it's going to make a couple of other recommendations to you as well. The first one it's going to make is that you should simulate this, right? So what you should do is have the model there making predictions, but then you should look at the actual results. Oh, the model said that this one was going to succeed, but it actually failed, right? And what percentage of that, how often is that happening where the model is making a bad prediction, right? Because the model continuously retrains itself, right? Out of the box, if you follow the Facebook instructions, it's going to tell you to run some training from some open source projects first to train up the model a certain way, and then actually to create an adversarial model internally. So I think they actually recommend 3 separate models competing against one another. And then it's going to recommend that, and again, the model is going to continuously retrain based on your own code, right? If you've been keeping a history of test behavior, which is something that we recommend as part of DPE, then you can even train that model on whatever test history that you may have currently available to you to make it even more accurate. But Facebook recommends having this simulator because you're going to be able to generate your own confidence score, right? Now, when you do things like you'll see in Facebook that they were stuck at like an 80% confidence, which is way too low, right? Nobody's gonna do this with an 80% confidence. And they looked at it, they're like, why? Why is this happening? They were training it with flaky tests, right? So it's a garbage in, garbage out kind of thing. So no wonder the percentage was low, right? If you're training a model saying like, oh, this test is going to succeed, or fail, and it's just flaky and it's total garbage, right? So what did they do? They turned on flaky test detection, and then they just filtered out any flaky tests that they discovered from actually training the model, right? And that got them boosted from like an 80% confidence up to like 99.5 or something ridiculous, right? I think Micronaut Foundation is like 99.9% confidence score right now. But this way, if you build a simulator first, you'll be able to, with confidence say like, okay, we're ready to turn this thing on. Also, set up a level of granularity where you can decide, I only want predicted to run against like this set of tests, right? Which is super easy to do if you're using something like Gradle, that gives you a lot of flexibility in the way that you're configuring your build. All right, we're not going to do the demo because I already know it's going to fail because of the network problem. But effectively, what you would be seeing in this demo, what we can do though, is that we can look at some of the public dashboards that we have here instead. Let's do that. So I mentioned that Micronaut has been using our version of predictive test selection. We have a whole program where we give Gradle Enterprise for free to open source projects. So if you have an interesting JVM-based open source project and you're interested in getting this for free, come talk to me as well. But let's look at what's happening here. So it's going to take a second to calculate because Micronaut runs so many builds. But we can see a few things here. We can see like, look at this, 99.5% confidence effectively right now that it's got. Now this fluctuates because it's constantly retraining itself. But we can see, that some of these individual goals we're actually doing test failure prediction on these things. So if I go and look at one of these, actual tests, like here's one that failed. We can look at our test output, and we can see, that we had tests that were set up and clean, and also ones that were failed. 73 failures in here. This one must not have actually been running predictive against it, though. This is the full test history that we have available to us, which is essential to being able to actually, have the predictive model. But we can see basically that. I want to run one of these that actually ran a test so that I can show you the explainability part here too. Let's see this. Not a great example. Maybe I shouldn't do a project called Foo, huh? Let's see. What are these people doing? There we go. Let's look at maybe sonar run here. Perfect. So this one ran with the selection turned on, and you can see the model is even telling us. Okay, well, it's telling us that the reason that it selected it. But in this case, it's because Micronaut hasn't updated to the newest version of the extension, so predictive is effectively not working. But this was the other thing that I really wanted to demonstrate, is that because you're using a gradient tree model to make decisions, that means that your model is highly explainable, right? You can easily determine why the model made the decision about a certain test that it made. And you should absolutely make that visible to developers, right? So that they can trust what's happening. So they can say, well, why did you skip this one? And then it'll give you a reason. Oh, well, because it ran under the same conditions 30 times and it succeeded every time, right? Something like that, right? So make sure when you're building this model that it's explainable as well. We're right at that 90-minute period. Let's take a 10-minute break. I'm going to see if I can improve my demos a little bit, or the network fabric here. We'll start back at 10 after the hour. Let's go ahead and get back to it. I'm sure the other folks will come back in. I want to revisit two things. First of all, the original local caching demo. My Mac decided to upgrade Gradle and didn't tell me, which is awesome. So I have reverted that. This project was built against Gradle 7 with a bunch of deprecations. So let's look at this again. I'm going to remove the local cache. It is blown away. I'm going to, let me make this a little bit bigger so it's easier for y'all to see. I'm going to run a clean build. Okay, so we had about a 5-second build time, 5 actionable tasks in this case. Taking 5 seconds, run it again with the cache. Look at that, 605 milliseconds, less than a second. So pretty good there. Maven, that's total user error on I just completely, much jet lagged or something like that. I was running Maven build, not install or verify. So good job, Justin. But if we do this the right way, do a Maven clean verify, that's the right command. So we had about a 5.5 or so second execution here without caching turned on. We'll run this again. And we only saved about 3 seconds from this one. But actually, we're going to revisit this one because I know why that we're actually getting cache misses. When we start looking at how we can diagnose cache misses, which is a little bit later in the lab, I'll show you exactly what's going on with this one. And the next thing I wanted to pull out was that I have a much better example of predicted test selection in action. This is for the Detect open source framework. And what I wanted to show you here was, you can see, for instance, that even though this one was selected, it thought for some reason that there was a high probability that the test would provide some useful signal. And so it made the decision to run. But the main thing I want to call out here is how explainable this is, right? And how important it is to have this explainability built in. Now, this is one that was selected, so it's not as scary, but let's look at a few of these that were not selected. So all of these tests, the machine learning is telling us, okay, well, I chose not to run this test, but why? Right here, the test recently passed with the exact same inputs, right? So it's telling you exactly why it decided not to select it, right? So this is really important. When you go in to build a model like this, the developers will really appreciate being able to see why a decision was made, and they'll be more likely to trust it. Okay, so that is my demo save. All right, so in conclusion, for this part of the workshop, I think we all hopefully have a broader perspective on why feedback cycles are important. Fast feedback cycles are important. The impact that they have on developer happiness and reduction of cognitive fatigue, and the ability to improve our throughput, which is the most important thing for an organization, as we've learned when we're thinking productivity-wise. And we've talked about 3 sort of force multipliers for this that also act in tandem. So if you think about it, a build cache is a great first hit. Let's say 20,000 tests need to be run, or Kafka, whatever we are. The build cache hits it first and says, okay, well, you only have to run 10,000 of those. Great. Cut the corpus in half. And then we run it through the predictive model and say, okay, of those 10,000, only 1,000 are going to produce useful signals. So eliminate the other 9,000 of them. Great. Now we're down to 1,000. And now let's run those in parallel. Let's distribute those tests and let them run in parallel. This is where we start getting 40, 50, 60x gains in performance on our build. Really staggering, right? When we look at all these three things, these three working together, it's a real powerhouse for acceleration. But then we need this part too, performance continuity, right? We have to make sure that we're constantly watching this stuff with analytics so that if the build is 15 seconds on Tuesday and it's 5 minutes on Thursday, we know that something happened in between that we need to investigate, right? So the continuity aspect of this is what we're going to kind of start to talk about a little bit when we get into the third section. For now, we're going to talk about inefficient troubleshooting of broken builds, pain point number 2. So what do we have? Inefficient troubleshooting. Why? Because when we go to troubleshoot builds, we often start with sort of a game of 20 questions, where it's like, okay, do I need to talk to the build engineer? Do I need to look in my own environment? Was this a CI build that failed? If so, where I can get information on how that build happened? Is there a build report? Okay, I got all that stuff, and I still don't know what went wrong because I don't know anything about the architecture, maybe, that the environment that this was running in. I don't know what version of the JDK it was running against. I have to go ask somebody, right? That's not fun, right? And that's not flow, right? That is toil, and it's friction, and it's frustration. So we want efficient troubleshooting. And how do we do this? With root cause analysis data, right? Better data about the build. Builds are really complex these days in a lot of cases, right? Especially Gradle builds. I mean, I love Gradle, but because you have the full power of Groovy or Kotlin available to you, you can really get yourself into some crazy snarls. But that's not just true for Gradle. I mean, I've seen super complicated Maven builds, super complicated Bazel builds, super complicated SBT builds, right? There's just more going on in the build that there used to be. So we need to get all of this data, all of this stuff that happened during the build. So yeah, most begins with troubleshooting. Helpers can burn out on helping. Impact analysis to any of this stuff is not data-driven. And this is where the CI teams really feel this stuff too, right? I mean, it's, we often as developers don't think enough, especially if we're dealing with like an integrated shared service CI, if we're working for a big company and we have like one CI that's sitting over like 300 teams. I mean, let's be honest, we don't think enough about our impact to CI, just as much as CI engineers don't think about developer experience enough, right? I mean, it's a two-way thing. But when we can improve our behavior as developers, then we're helping in CI. And when the folks in CI can give us better data in a self-service fashion, then we can troubleshoot our stuff faster. We don't have to rely on CI engineers as much, right? So we need to be thinking about this stuff. So the only way to really effectively diagnose flaky issues is to capture data from every single build that's run, whether locally or in CI or in remote workstations. And it has to be comprehensive to allow for full root cause analysis without having to reproduce the issue. Because how often is that? Oh, well, can you reproduce it? Oh, yeah, sure, but it took an hour last time, so I'm just going to have to wait another hour and reproduce this thing. Having all of that data available to you in one place, from the time that it actually ran the build, like a record of that build, allows for self-service impact analysis, okay? And so self-service or collaborative build debugging, because these interfaces, if you build something like this, it should be easy to share, right? It should be very easy for you to point at one place in the interface and create a link or something that you can pass to someone else and say, hey, this is exactly what I want you to look at, right? Because you're going to have a lot of data in here if you do this right? So it's going to be good for that data to be easy to share with somebody else if you want to collaborate with them. So what we offer is a thing called a build scan. Anybody run a Gradle build scan before, a Maven build scan before? All right, cool, a few of you. I love this function. Before I even came to work at Gradle, I was running Gradle build scans back when I was doing Android development and stuff because it's super helpful. It's a freemium offering. You can do this for free. Some people are blatantly abusing it. We don't really care. Grubhub is running like 5,000 build scans a day, like free ones through their automation. And they've even set up automation to auto purge build scans and stuff. We're like, hey, fine, use it. So we don't care. Go crazy if you want to play with it. If you don't really care, or you don't want Gradle Enterprise, or you don't have Maven or Gradle or any of these things, maybe you're a JavaScript shop or a .NET shop or something like that. At least look at these as kind of inspiration to be like, oh, okay, this is some really good data that if we were doing this ourselves, this is the critical stuff that we should be pulling into this troubleshooting, self-service troubleshooting interface that we want. So this is not about pushing build scans on you. I really do legitimately believe that they're very valuable. But at the very least, if you're either not JVM or you don't want to use this stuff, look at a few of them. And I'm going to give you some resources where you can pick through and look at some at your leisure. But it'll give you an idea of like what data is really important to improve troubleshooting. So like for us, we capture a lot of stuff. Full console log, which is searchable and filterable and shareable and all that kind of stuff. Failure data, a full timeline of the build, which is especially important if you're using any type of parallelism in your build to be able to pull out, okay, well, this was actually the critical path, and this was all the stuff that was running in parallel. It can be really hard to glean from console log data, but visualizing it really helps. Deep performance insights about cache behavior and dependency downloading, all this kind of stuff. Where is the build spending its time? Which projects were involved, which tests were run, and what was their output, dependencies, extensions, plugins, custom values. So people use custom values for all kinds of weird stuff. Major US credit card company processor switched recently from Jenkins to GitHub Actions, and all of a sudden saw their build times really sink. They didn't really understand what was going on, so they looked at a build scan. And the first thing they noticed was that dependencies were taking forever to download because they forgot to hook this thing up to their Artifactory. So that helped. But then it was still slow, still slower than when they were running with Jenkins. So then they did something really weird. They used a custom value in the build to scrape IOStat output from the environment, like so disk fabric output from the environment, and stuck it in the build scan, and found out that the disk was slow in this ephemeral environment that they were using. And so they improved their storage fabric and sped up their builds, right? But that, I mean, think about how hard that would be to diagnose, and how many people would have to be involved if you weren't collecting that type of data at build time. Configuration switches that may have been set, and infrastructure details, the operating system architecture, the JVM major version, those sorts of things. And when you've got, so this is Spring, who uses our stuff for free. You have this nice interface where you can see them all sort of in a single view. So if you create something like this, you want to be able to easily show an inventory of it and make it filterable, so you can look at, maybe I just want to look at all the failed builds or something like that, or maybe I only want to look at builds from this one project. But it's nice to have sort of this summary view as well. Another just shot, the infrastructure stuff right here is surprisingly useful, even though this looks like very basic information. And if you were running stuff locally on your laptop, this is going to be easy data to get. You probably know what's going on. If this is running in some ephemeral CI environment out in the cloud, it's going to be really hard to figure out some of these details, right? We capture that right into this interface so that you can use it for self-service troubleshooting. Build scan comparisons. So, super cool. Once you've got a canonical data format for all the stuff that you're scraping for each build in your standard, you can start comparing them, all right? So then you got a build that succeeded and a build that failed under what seem to be the same conditions. Normally, I'm going to have to go through in my head and, okay, well, did they do the same this? Did I have the same that? Did I do this? Did I do that? But when you can compare the data sets, then things get really powerful. You can look at a failed build and a successful build and immediately see what was the difference between those two builds and what could have caused it to fail. All right, so really, really helpful. So let's explore some of this data. Let's just look at some interesting Spring builds for this one. So by the way, these are all public dashboards, and I'm going to give you a link at the end of this where you can, there's 18 of these things that are just running against various open source projects. They're totally public, so it's great to go and pick through and be like, oh, I think we should be doing this. Oh, I think we should be looking at that, right? So these are all representative of a single build. So the first thing that they're doing that's great is tracking local build times, right? But we're tracking a lot more than just that. But this is data that's absolutely getting included in the build scan. So we can see how long it took, and we can even see how many builds were run, and we can filter this down. Was this a CI user, right? Maybe we just want to look at CI builds, so we can look at builds that are tagged as CI, or maybe we want to look at local builds. You know, we can refresh and just look at the builds that were run by individual users locally, right? So a lot of great data in here. And then let's look at one, okay, a Spring Boot build that failed after 16 minutes, right? What went wrong? Well, look at all the data that we have in here to help us figure this out. And again, totally self-service to the developer, right? So you're a developer, you just ran Spring Boot build, it failed, and you have this interface immediately available to you as part of the build, the build report. So you can start digging through it and figuring out, what went wrong. So we have like a nice summary of stuff, great. But let's start digging in. So the console log, it's important, we should have it in here. But it should also be pretty easy to navigate. So we should be able to, for instance, filter down to just a single task if we want to see output from, I don't know, process test resources or something like that. Oh, it's not very interesting. But we can, just filter down to stuff that happened within a single task or task type, right? Maybe we want to see what was going on with our tests. So we can just look at the console log output that's related to tests. And all this is shareable. So let's say that I wanted to point this out to somebody. Maybe I'm working in pair. Look what this did. It creates sort of a custom link that I could then pass to somebody. And it's going to take them right to the area in the interface that I want to draw their attention to. Okay, so whatever you build should be shareable like this, because this is about self-service, but it's also about collaboration if you're working with multiple developers on the same problem. This build failed, so we can get our full kind of failure analysis here, and we can look at a failure history because we're aggregating this data. So we can actually see, oh wow, this one failure impacted 5 users over the last week, and 44 builds, right? So there was actually some impact here. Right? We're gonna dig back into this one a little later, but we can link right to a full failure history from there. If there were any deprecations in the build, this was stuff that was breaking in my own build because my Mac decided that Gradle 8 would be fine and it didn't need to tell me that. But you can see here that these folks now know exactly what they would need to do from this build in order to get it ready for an upgrade. So very useful for upgrading, right? Because it's just, we now have a checklist of stuff that needs to be addressed before we can comfortably move to the next version. Timeline, gotta love this view, because again, so hard to understand tasks that are operating in parallel. But we can really zoom in on here and we can see exactly what tasks are executing. And we can do cool stuff too, like, we can say, what's the longest task? Right? This one right here, which by the way failed. So now we've got this, task that took 15 minutes that just failed. Deep performance insights, total build time, total execution time, garbage collection time, the peak memory usage that was in effect while the build was happening, so that we can see maybe part of why our build is slow is we're not giving it enough resources. Right? The configuration, so this is actually the time it took for the build tool to scrape its own configuration and deciding on what it needs to do, which is pretty fast in this case. But the whole reason we introduced a configuration cache is because there are really complex builds that can take 20, 30 seconds just to read the configuration. Right? Total tasks executed. How long was spent resolving dependencies? All right, also very good information to have. How many tasks came from cache that were avoided for various reasons, and we can drill down to this too, into the timeline and see what executed from cache. By the way, this timeline is a great place to see how optimal your cache is, because we can just say, what's supposed to be cacheable here that we ran? Oh, look at all this stuff. There's a lot of work to be done here now, because theoretically, all of these tasks should be cacheable, but we ran them anyway. So this is a lot of the optimization for cache, is coming into an interface like this and saying, okay, well, I got these 15 tasks that I should be benefiting from cache, but they're not for some reason, so I need to look into it. All the build cache details, hits, misses, packing and unpacking of the cache, right? So all of this information should be available as well. In this case, the Gradle daemon, how long has it been running? How many runs have done from this daemon? Gradle has its daemon that's constantly running. Where did it download all the dependencies from? And how long did it take? Where did stuff come from? So you've even, I hesitate to use it, but you've almost got a bit of a bill of materials in here too. Full details on the tests, right? Including, again, the ability to filter down to a single test class, or maybe I only want to look at failed tests. Maybe I only look at flaky tests. Spring doesn't have a lot of those because they proactively deal with them. But again, very nice to be able to see, all of these details quickly in the build. What projects were built and what sub-projects were included. A full dependency graph with versions and even with information on why, what variants were selected. So this was selected as part of the runtime. And what type of attributes does it have? What depends on this dependency? Why is this getting pulled in? What required it, right? So full dependency graph is available here too. Dependencies that were specific to the build as opposed to specific to the application. Any plugins that may have been used during the build and the details in here. Again, custom values. A lot of folks like to do simple stuff like recording the git commit so that you can group build scans according to a single commit. Right, very useful. Any configuration switches that were used during this build. So like, for instance, we can see the build cache was turned on, and this links right to the documentation. So a developer, if they're curious about any of this stuff, they can go right to it. And then finally, these infrastructure details. So the operating system, CPU cores, what version of Java were we running? In this case, it was Bell's Liberica OpenJDK. What was the locale? This has caused problems for people before, like running the build in the wrong locale. And that can also be hard to determine. What default character set was used, right? What was the public host name for the build? So again, really good in-depth stuff here. And an interface like this does two things for you. First of all, it's a great way to help developers in a self-service manner be able to troubleshoot, but it's also a great way to capture all this information that we've been talking about so that you can aggregate some of that information, right? Like local build times, like failure rates, and that sort of thing. Okay, how are we doing on time? Less than an hour, about 40 slides to go. I think we'll be just fine. Probably have time for questions too. Okay. Like I mentioned, these things can be extended, and yours should be extensible too. You should be able to tag these things and attach links to them or whatnot. Okay, so that is more efficient troubleshooting, and we went through acceleration. So we've covered really two legs of the 5 pillars at this point, but the rest of them are a little bit easier to explain in the acceleration stuff. So we've hit acceleration, and now we've seen ways that we can make our troubleshooting more efficient. Okay. But what about problems that have occurred that we could have dealt with proactively if we had just been observing them? So let's talk about pain point number 3, flaky tests and other avoidable failures. I love this quote, and it sums up so much of the essence of DPE and why we need it. Yogi Berra, catcher and baseball philosopher, said something just so simple. You can observe a lot just by watching, but nobody's watching. That's the problem. We want to eliminate avoidable failures for our developers, right? And we can do this by just doing simple things like aggregating failure data. So we saw this dashboard just a moment ago when we looked at a failure history. But once you're capturing failure data, so once you're capturing, hey, this build failed and it failed for this reason, well, you can start doing some interesting things. Like, for instance, you can keep track of how many times that exact failure was encountered, right? And then you can make that easy decision. Okay, I asked earlier the question, I've got an hour to improve my tool chain. What should I work on, right? Well, right now, it's usually, well, how many emails did I get from the developer about this thing? Okay, I'm probably going to just help this person out because they're very loud, right, and causing me a lot of headaches. But that's not good, right? Because that developer could be totally wrong. They might think they have the worst problem in the world, but it turns out that it's only impacting them, right? But with data like this, you can say, okay, where can we make the biggest impact, right? Which failures are impacting the most developers, the most builds, so that we can start eliminating those failures first, right? And you can do that with an interface like this, just aggregating all that failure data up. Anybody familiar with Open Rewrite and Modern? All right, so Open Rewrite is super cool. You should go check them out. They're Modern is a small startup at this point. They're in their Series A. I'm convinced they're going to the moon. Open Rewrite allows you to write flexible code translation recipes and then make these code changes automatically at scale. And I'm getting somewhere with this. The first application for this was, hey, we just found this vulnerability in this open source library matching this pattern of code, right? Maybe, I don't know, it opens up capability for a Stack Overflow or remote code execution or something like that. And we can easily recognize that it's this pattern of code that causes this vulnerability. Let's go use CodeQL to search for that in every other package that's available on GitHub, and then let's use Open Rewrite to auto-remediate those issues, right? So the first time they did this, they got like in a lot of trouble because they issued like 15,000 pull requests against all these different open source projects like all at once, and they're like, what are you doing? But it ended up being actually very effective. So what are they working on now? Well, they're using failure analytics. They're doing this against close to 35,000 open source projects now, and they have motivation to move this to 60,000. So you can imagine that every time they make one of these changes, a lot of the builds fail, and it's hard at that scale to have a single interface that can show which builds are failing as a result of this change. So they use failure analytics, their own kind of version of failure analytics, to do this, and now they're doing something really cool. They're grouping these failures together. They're calculating vector distances between the failures, so like how close are these error messages, and grouping those together, and then they're using ChatGPT to have it read all of those failures and give it a theme for the failures. Like it's using a large language model to actually read the failures and then reinterpret them and say, oh, these all seem to be failures from using the wrong version of Java. These all seem to be failures from non-verification thing like bad infrastructure against an integration test or something like that. It's very, very cool what they're doing. I'm convinced that this mid-step that we have right now with like SBOMs and scanning tools, I think it's just a mid-step. I think what you're going to actually see is software scanners that go in, find the vulnerability, and then use open rewrite rules or something similar to auto-remediate the fix right then and there and issue a pull request automatically. It's very, very cool. You should definitely take a look at what they're doing. But failure analytics are critical to this process that they're doing. You wouldn't be able to do it at this scale without failure analytics. And then dealing with flaky tests. Well, this is how we deal with them right now. We try it again, and then we rerun it, and then we rerun it again, and then we just ignore it and improve the pull request anyway. Pretty much do all those things. A couple of problems with this. First of all, we are definitely introducing bugs, right? We know it. It's definitely a code quality issue here. But this is also terrible for CI, right? Poor CI folks are getting 20 build requests for something that if the test hadn't been flaky, they only would have gotten one, right? So we need to deal with this too. So DPE organizations analyze flaky tests. You can see here, this is an analysis of a single test. Which one is this? This is one of Gradle's, from the Gradle build tool. And we can see that it was flaky 90% of the time over the last, whatever this is, week, I guess, 90% of the time over the last week, this test was flaky. Maybe we should do something about that. Our build tool engineers, and not just stuff at Gradle build tool, I mean our Gradle Enterprise and Gradle build tool folks have this practice, but they're doing this also at Netflix, LinkedIn, Twitter. They schedule what they call flaky test days, where they just open up their test dashboard and then sort by flakiness, and they just start at the top. Eliminate, 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 eliminate. So again, you have an hour to improve your build tool chain. Where do you focus? This type of data lets you make very educated decisions about how you can make the most impact to developers, right? You can detect flaky tests in a number of ways. If you're using build caching, it's actually easy. Think about it. What is that build cache doing? Generating a cache key based on a very specific set of inputs if anything changes, the slightest thing changes, you get a new cache key. So I got a cache key that's matching a test task that failed, and then the same cache key test task succeeded. Flaky, right? Under the exact same conditions, that test is non-deterministic. Sometimes it's failing, sometimes it's succeeding, so it's flaky. If you're not using caching, unfortunately, the best mechanism right now seems to be create a plugin that automatically reruns the test once or even twice, And if it's red, red, green, mark it as flaky. Is that as efficient? No, not at all, right? Caching and that method of detection is way more effective, or I say way more efficient. But they both work. And at the end of the day, even retrying those tests a few times, as long as you proactively eliminate that flakiness afterwards, it's worth it. It's worth that extra bit of resource up front so that you can fix the problem long term, okay? Flaky builds and tests are absolutely maddening, which we know. And the thing is, too, that failures, they're often broken down into different types of failures that we should consider. The verification failures, as they're typically called, are things that are sort of expected or planned for, right? So a syntax error, or a test assertion that failed, right? But something that we're like, okay, something could go wrong here and I want to handle it somehow, right? Non-verification failures are where things tend to get difficult. Flaky tests, for instance, but also maybe a binary repository is down, or some OOM exception when running the build, or you're hitting an API to do an integration test and you're getting 500 errors, right? These can be a little harder because they're not necessarily expected as part of your own workflow, but they definitely are impacting you. And these are ones that are harder to visualize without aggregating them too. So what we generally recommend is that you come up with a method of failure analytics where you're actually able to tag individual failures once you start discovering them. Be like, okay, this was a verification failure, this was a non-verification failure. Why? Because then it's really easy to figure out who to blame, right? If it's a verification failure, it's probably the developer's fault. If it's a non-verification failure, it's probably build engineer, CI engineer, infrastructure, right? That alone reduces a ton of cognitive load in troubleshooting, because that's often the first step. Like, whose fault is this, right? And we need data to get that. Which again, makes this type of stuff makes triaging and prioritization difficult, because it's non-verification failures can mask sometimes as a verification failure, as in like a flaky test. A verification failure can mask as a non-verification failure. So maybe something like you're pulling a dependency snapshot and it's the wrong version. So these can be, flaky and hard to reproduce without analytics, right? So aggregating this stuff up, which again, if you're capturing build data like a build scan style thing, it becomes easy. It becomes easy to understand how to do this. Just stick it in a database and run some analytics against it. Okay, so let's look a little bit at the details that we have around flakiness. So we're going to go back to our Spring dashboard here. And we're going to look at tests. And we can see here, look what's happening. Spring is aggregating all of this data up. So when tests either fail or when they're flaky, they're keeping track of all this and they're putting it on a dashboard. Then they have the ability to come in here and say, okay, this test was flaky. And they're actually pretty healthy right now, but I've seen them sometimes where they're like 20%, 30%. But they must have recently had a flaky test day. They literally would just go, open up the dashboard, sort by test flakiness, and start at the top, right? So Couchbase test integration tests. It's an integration test, right? Probably having some non-verification issue. We need to beef up the Couchbase server or whatever it is. Notice a theme here, right? DevTools integration, Elasticsearch, Cassandra, right? So a lot of these things that are flaky are based on external infrastructure, right? But again, difficult to glean without having these types of analytics, right? You should also be able to drill down to a single test class and be able to see sort of a history of behavior so that you know if you fixed it, right? And it's also helpful to be able to have some of this execution time to help you think about impact, right? I mean, if I'm making the decision between fixing 2 flaky tests and one of those tests takes 30 minutes to execute and the other one takes 2 seconds, right? Well, let's fix the 30-minute one, right? Because that's the one that's actually wasting the most time for people. All right, that's basically what I wanted to say about that. Okay. So we looked at flaky builds. What about no metrics or the ability to observe KPIs? This is where that first question, are you tracking local build times, becomes relevant. Because it's a 3,000-year-old adage that's just as true today as it was 3,000 years ago, and that is what gets measured gets improved, right? That's why I make the recommendation that if you do one thing when you leave today, it's to start tracking local build times, right? Because once you're observing those things, I promise you it's going to cascade into other improvements that you just didn't think about. I mean, it's just, like when I say that nobody raises their hands around tracking local builds, I really mean that. It's not like a thing to feel bad about, because for some reason as an industry, like, we just haven't woken up to this. It's just we just think that this is how things have to be, and we just don't think to improve this stuff. It just doesn't come naturally to us. I was at a DevOps Days, Aarhus, Denmark, doing a stand-up, a keynote, and I had a developer, or a DevOps person, come up to me afterwards, DevOps engineer, and they were like, that was one of the best talks I've heard in a long time, but it was also one of the most frustrating talks that I've heard in a long time, because I'm listening to your advice and kicking myself that we weren't doing this 5 years ago. Like, why weren't we doing this stuff? I'm like, I don't know, but now you know. And so it's going to be very difficult, sorry, to leave this room and not be thinking about this stuff because of this question. So DPE organizations, they do this. Right here, what you're looking at a representation of is all the builds. In this case, was the Gradle build tool. Was it? Yeah, I think, maybe not though. Either way, you can see every single build, that's what these bars are representative of, that took place over this period of time. And you can see serial execution time versus actual wall clock build time. We can see our avoidance savings, any overhead that was introduced by the cache. So we can trend this stuff, right? We can take a real look at it, put it on a graph, and see how consistent we are. Because without focus, we know that problems can sneak right back in, right? You may have done a great job optimizing your build, getting it down to 5 seconds, and then something happens with your caching, stops working, or you introduce a new annotation processor, and suddenly it takes twice as long to run your compiles than it did before. Code refactoring, new office locations with people going back to hybrid or even in-office work now. You may have bandwidth issues that were different at your house than your office, and you need to keep track of that, right, so that we can understand it. Because it's really impossible without observability to have like a consistent, great, and fast developer experience, right? Because how do we know? Like, we don't have the data to say whether the experience is good or bad. What happens today with most regressions? Nothing. They just kind of go unnoticed. They slowly creep up. The build was 15 seconds last month. Now it's 10 minutes. Why? Well, I don't know. Look at this graph. Every 2 days it got another 5 seconds, another 10 seconds here, right? Just small incremental regressions that can lead, into very big problems. So sometimes they go noticed, but they go unreported. Sometimes they're reported, but they're not addressed because the root cause is hard to detect. We don't know when the regression was introduced, so we don't even really know where to look. And they're only escalated after they've already caused a lot of pain, right? So again, I've said it a million times, but this is all about, as much as possible, reducing this pain, right? Reducing this friction, keeping developers in a state of flow. And the only way that we can be sure that that's happening consistently is by tracking this type of data. So significant regressions can be detected quickly. And then with that available data, we can often easily detect the root cause. If we know the window of time that the regression took place, there's only so many changes that would have happened in the mid-time that could have caused that, right? So it's usually easier to determine this. Having data from all the builds allows for a data-based prioritization and performance-related improvements. So this is what we said before. If you have an hour to improve the build, where should you spend your time? With analytics, it's gonna be an easy decision. Build scans provide this capability. Fewer incidents and builds that are getting continuously faster. Builds that are getting continuously faster as opposed to continuously slower. All right, so let's just take a look at what some of this what are the important bits of data that we should be looking at? And also, we're going to go through an interactive scenario of actually like looking at a build that's not optimized for cache and showing like how we could kind of deal with that. So we'll look at both of those in the same demo. So going back to performance, and this is the Spring dashboard again. Look at what they're recording here. So this is over the last 7 days, over the last week, and we can kind of zoom out a little bit. There we go. And we can kind of drag this thing around to focus on different areas of the graph. But we're looking at the last 7 days of builds from Spring. We can see that they've had 2,698 builds in the last week. And we can see that their avoidance savings on average, now this is for all projects, I could drill down to specific ones, which we will in a second actually. But avoidance savings for all projects have been about 7 minutes, 41 seconds. So here's our ROI. 7 minutes, 41 seconds times 2,698 builds. Easy, right? So not a hard thing to sell to your boss. If we want to drill down to a specific project, then we can say, okay, this was for the Spring Boot project. Now they're seeing significant savings, right? They're actually seeing savings from their remote build cache of 25 minutes on average per build. And then you can do the math there against 477 builds in the last week to figure out. But when we start getting down into even more kind of more specific things, like we want to see maybe CI builds that were successful in the Spring Boot project that were just the build task, then we can start seeing things that are a little bit more consistent. So we have some weird outliers here. We could look into kind of why. We saw that there was a big performance savings here from avoidance savings. And we can even compare these two things because each of these are representative of a build that we can just go look at the build scan for. Like I can go right to here and see the full build scan from this graph, figure out why it might be an outlier. And then we can also put all this stuff into a trend. So notice here we're looking at these 5 metrics. We're looking at total build time, serial execution time. So this is wall clock versus all the tasks that were executed, some of these in parallel. And we can even see our parallel factor here is 2.96, right? So if we divide this by 2.96, we should come up with our build time basically. We can see that, on average here we had the hour and 34 minutes of avoidance savings. Build cache overhead, so 30 seconds of build cache overhead, but I'll take that over an hour and a half any day. And then 5 minutes on average downloading dependencies. So these are the 5 metrics, and we just have them visible in 2 different ways, right? Same metrics here, build time, serial execution, but this is where we start getting a really nice ability to look for major regressions in performance and see exactly where they took place, right? And then start diving into those build and that build data to figure out what's happened. Why is this taking longer? Where is this build spending all of its time? Same with avoidance savings. We like to see this go up, which it's kind of doing here. Build cache overhead, and then of course our time dependency downloading. So we want to be able to not only capture this stuff and look at it easily, but you also want to be able to trend it, okay? So that's one thing. Then the next thing I want to show is what happens when we actually have, okay, this build was doing great, and all of a sudden we're seeing a cache miss. Let's do this for, let's do it for Maven. Actually, how many Maven users in the room? How many Gradle users in the room? Okay, we'll do Maven. So we're going to do a Maven clean verify of this build. Oh, we're going to try to. Maybe we'll be doing a Maven build. Oh, no, that's easy. My Mac also decided to upgrade Java to 20. It keeps putting on breaking changes. Okay, so now it's running a normal build. Great, 8 goals, 8 executed. Let's run this again, see what kind of cache savings we get. well, nothing came from cache in this point, so. It's the people at the training server. Yep, that's what it is. So I can't authenticate against the server that this one wants to entitle for the build cache, but I'll show you kind of an example of something that could mess us up. So normally what I'd be able to do is put these two things side by side, but I'm not going to go through and figure out the new password and make you wait for all that stuff. What we would see is that one out of the 3 tasks here, or goals, should have been cacheable. So going back into this interface where we see, okay, here's our timeline, and then we search for things that should be cacheable, but they ran anyway, right? So we don't have any here, but you know, if in this case, what you would see is that, you know, we had 3 tasks that should be cacheable, but one of them was not pulled from cache. We got a cache miss on that, right? And what you would see in the build comparison is that the build is actually creating, running a little Groovy script here. And when we look at what that Groovy script is doing, it's creating a timestamp in a file called timestamp.properties, right? So we can see here, you know, source main resources. This timestamp shows up, and of course this timestamp is going to be different on every build. So of course it's going to change our inputs and generate a different cache key, right? But it's very, normally when they don't change my password on me, easy to just line these two things up, because what you would see is that you would look at all the goal inputs and you would say, hey, the goal inputs were different on this one task. What was different? Oh, this timestamp.properties file was different between the two of them. Great, I better go either normalize that or ignore it for caching purposes, or see if I even need to generate this timestamp, right? I should go deal with it somehow. All right, let's wrap this up. Make sure we have some time for questions. Okay, so we've covered almost all of the pillars here. And really, at this point, have covered the pillars that are specific to productivity and I think most acutely felt by developers. So we've talked about the 3 acceleration technologies that can be used in tandem to get 40, 50, 60x gains. We talked about build scans, which can make self-service troubleshooting a lot easier, and also collaborative troubleshooting a lot easier. We looked at failure and flaky test analytics, which personally is my favorite part of DPE, because we are completely eliminating problems for developers. They never even have to run into them in the first place, right? And then we talked about how it's important to have metrics and KPIs around this performance so that we can detect regressions and proactively deal with those things. So the final one then, which bears mentioning, but is arguably less productivity focused, is the impact that all of this is going to have on CI. I mean, really look at what happens. It was really very simple. When we are running builds less, even if we're running builds more frequently, but they're not taking as long, then agents aren't going to be queuing as long. When we have eliminated flaky tests and avoidable failures, then the developers aren't clicking run over and over again and scheduling all these jobs to run in CI. So our pipelines are more optimal. Now, not necessarily cheaper, right? We're talking about efficiency. But what would we say earlier? What do developers tend to do when cycle times are faster? Run their builds more often, right? So you may see more jobs running in CI, but those jobs are going to be more valuable, right? They're going to be more valuable. And then with the self-service troubleshooting, we also see that reduction on support impact for CI engineers, right? So if developers aren't opening tickets every time a build fails because they don't have visibility into the CI environment, then that significantly reduces the support load on CI engineers and allows them to focus more on continual improvement. So more idle wait time for developers when CI is underutilized, because a lot of times developers would rather do things locally because the state of the CI is so bad. I've seen both cases, right, where developers are like, oh, the CI environment's way faster, way beefier than my laptop, so I'm going to do as many builds as I can in CI because they happen faster in there. But that's no good for the CI engineers either, right? We want to do as much stuff local as possible, right? That's key to this stuff. Decreased agent availability, resource efficiency, and then more engineering time required on infrastructure provisioning maintenance. So we want faster CI pipelines using build caching. Remember, again, we saw the nice architecture where we have CI actually populating a remote cache, which works great for ephemeral nodes. Faster CI pipelines using distributed testing and predictive test selection. Again, all this stuff, yes, it works locally, but it works in CI too, right? So CI is going to be able to optimize the test set using predictive, and it's going to be able to distribute its tests in parallel if it wants to. Increase reliability in general with flaky test analysis, and then getting ahead of build regressions with trends and insights. Okay, so kind of in summary, what should you be doing? Well, these are the pain points that you should be focusing on. Idle and wait time for developers. We want faster feedback cycles. And now we see that we've got build cache, distributed testing, and predictive test selection that can help us with the acceleration. What do we have? Inefficient troubleshooting. And what do we want? Faster troubleshooting with root cause analysis data. In our case, build scans. But again, those can either, please use them, they're wonderful tools and they're free, but you can also use them for inspiration if you don't have JVM compatible projects. Flaky tests, we want reliable builds and tests, so we have failure analytics to deal with that, right? So take the failures. If you're already thinking about how you could build this interface, then also be thinking about how you can aggregate the important data that's in that interface, like the failures and flaky tests. And then how you can aggregate that data into trends and insights so that we can see how things are performing en masse. What do we have? Inefficient use of CI resources. What do we want? CI cost and resource efficiency, build cache, resource profiling, failure analytics, and the test distribution and predictive test selection. All of these things improving CI. All right, where do we go from here? Well, I mentioned this before, I'll mention it again. The best DPE organizations build focus teams. If you go to our Gradle website, Gradle.com, in our Learning Center, which I'll send you a link to in a moment, we have something called the DPE maturity model. And it takes us through what we call the lowest compliance with DPE or idling, all the way up to DPE at scale, which is the kind of the fifth level of your DPE maturity. I really recommend that you look at this matrix. It's a great way to just kind of self-diagnose and say, okay, I think we're like at this stage with DPE right now, but then you'll have a very clear path. Okay, well, these are the next things that we have to do to get to the next level of maturity with our own DPE practice, right? Now, all of these businesses that I point out here are what I would call scaled DPE organizations because they have dedicated teams, right? They have built their own center of excellence around DPE. They have people that are called developer productivity engineers. A lot of them used to be platform engineers. They're now developer productivity engineers, and this is all they focus on. They look at the dashboards. They look at the failure analytics. They make direction on which parts of the build should be improved. And again, I just really want to underscore the effectiveness of this when you have people who were developers and have empathy for the developer experience, right? That creates urgency around this. If you have someone like that on this team and they notice a performance regression, they immediately can resonate with the pain that that's causing, right? It's not just a number. It's oh, wow, this is a developer's time being wasted, right? That's a colleague who's working on the same mission as I am. I need to do something about this, right? That's the importance of the human aspect of DPE teams. I know I said it before, but I'll say it again. It's one of the big differences between DevOps and DPE. If you want to join us, talk to me, talk to other folks, we have a whole developer productivity engineering channel in our community Slack, which you are welcome to join. If you're a Gradle fan, we also have a bunch of the Gradle build engineers are in this Slack, and they love to communicate, talk about the build tool. We employ close to 30 full-time Gradle build tool engineers, and they're all available to talk with in here. We also employ some Maven engineers, some Bazel engineers, and we just made our first acquisition of a company called Triple Quote, which has an acceleration technology for the SBT build tool. So we're going to have some SBT experts in there pretty soon as well. And I'm usually hanging out there too. If 3 hours with me was not enough, you can find me in there. This is our Learning Center. Tons of great free information in here. You'll find videos, white papers, testimonials, blogs, all kinds of stuff. This DPE showdown, this is a lot of fun. There's a show in the US on ESPN, I'm not a sports guy, but I just happen to know that this exists, where they basically have, so sports commentators will answer questions about sports. I'm like reaching here because I really don't know anything about sports, but they'll ask questions about, hey, how this player was doing this thing. And then the audience can vote live on who they thought gave the best commentary, right? So we made a version of this for DPE. We bring in, every 2 months probably, 4 developer productivity engineers from other companies, right? We bring them from all over the place. And we do the same thing, same setup, right? Audience, usually 300 or 400 people in there, usually draws pretty good crowd. And we ask them questions, and then the audience can vote on who they thought gave the best answers, and we all have a lot of fun. And you'll learn a lot about how other businesses are doing developer productivity engineering. So I really recommend the Showdown. We also have that version of it called the Lowdown, which is just a one-on-one, more like a fireside chat. So this is where that great quote from Danny Thomas about the amount of toil and friction and frustration that engineers are willing to put up with, right? That came out of one of the Lowdown interviews that we did with that. So we really bring in these great developer productivity luminaries. We sit down with them for an hour. We ask them questions, their success stories, and things like that. So a lot to be learned there too. We have a book. You'll see Gradle's logo on the front of it, and that's it. The rest of it is completely vendor agnostic. It is an 81-page manual on developer productivity engineering. It's in its second revision. We are working on getting a physical copy of this thing, but for now, it's an ebook. This will break down in great detail even more of what we discussed today. You'll look at a lot of case study-driven stuff and get into really a deeper vein of everything that we've kind of discussed today. And then if you're up for a challenge, this is what I mentioned earlier. Now I got my demo fixed, so I was able to save face there, but this is still a lot of fun. You can go through, hook up either your own project or some open source project if you're not comfortable uploading your own project into the public BuildScan server. And you'll basically, and there's instructions for Gradle and for Maven. You'll hook it up to a real instance. You will run the build twice and see your cache savings. And then if you so choose, you can take a screenshot of the build scan with the cache savings and send it to us, and we'll send you a nice little swag kit in the mail with Gradle socks and mugs and stickers and all that stuff. Oh, and then visit our booth, for sure. We're right at the front of the expo as you walk in from the opposite side. So, coming out of this room, you'll come out, take a right, go all the way down to the end, and on the left, you'll find the Gradle booth, big Gradle Enterprise banner there. So you can get some Gradle swag. Our famous t-shirts, we got this one. What did we bring, Hugh? We brought Kiss My Cash, and I think Cash Me If You Can. Which one have you got, Hugh? Yeah. So yeah, come by and grab one of our t-shirts, have some excellent conversation, and maybe get a Gradle Enterprise demo if you want. And that's it. So we have plenty of time for questions. We got 20 minutes or so. So go for it. Oh, thank you. Thank you, I appreciate that. Do we have any questions? Yeah, sure. Sorry, I think so. I'll repeat it too. That's a great question. So the practice is agnostic to any language, right? So this is where you would want to kind of do your own research and see, okay, what can I do here? Do I have a build cache? Can I detect flaky tests? Can I aggregate failures? You may end up writing some of your own logic, but there are also other companies that are out here doing this. So as far as like the direct demos that I showed you, that's all very JVM centric. We're Gradle, we're a JVM centric company. But the practice of DPE goes well beyond any one company. There's about 25 folks in this space now, actually, which is great for me. That means that I'm doing something right, because when I first came on, I think there were about 10 people in the space, maybe only a couple that were directly competing with us. And now I've got like 25 direct competitors, which is awesome, right? I mean, we're trying to give validation to this practice. So another great one to check out if you are using Python or JavaScript is a company called DX at getDX.com. And this was Nicole Forsgren's new company. So she's the one who invented Dora, sold Dora to Google, and then wrote the book Accelerate. And like, this is her new company. So if you're using like a more scripty type of language, you could check them out. But you know, kind of do some research. So yeah, again, the question being, you know, does DPE apply to things beyond the Java world? And absolutely, yes. We get a lot of questions about .NET as well. We're such a Java-focused company. Like, people are like, hey, are you going to release anything for .NET? And I'm like, I think if we did, it would be bad. Like, we don't have that spirit inside the company. So maybe one of you could start a .NET DPE company and we could buy you. I'm just saying. So, but yeah, do the research. But this practice absolutely applies to every software organization. And because it consistently increases throughput and decreases cost in every case, it's not just for Bay Area tech companies, right? It really is for everybody. I mean, the Bay Area tech companies are the first ones to start putting this stuff to practice, but that was only like 5 or 6 years ago. Netflix put their productivity team together in 2017. So you haven't missed the boat on this, which is kind of exciting too, because think about it from a career path perspective. Like, what if you were the person who brought DevOps into your organization 5 years ago? What does that do for your career, right? But the good news is now you can be the person who brings DPE into your organization, right? Because it is still kind of new. But yeah, decreases cost and increases throughput in every case, which means it's pretty much universally applicable. I've never seen anyone who implemented this who's like, oh, it makes stuff worse. It's like pretty much always makes stuff way better. Any other questions? All right, well, if you think of something later, feel free to reach out, email me, or hit me up on LinkedIn, or come find me in the booth. Happy to talk about this stuff. Hugh knows that I will talk ad nauseum if you let me about this stuff. So, all right, well, thanks. I really appreciate the time, and enjoy the rest of the show. Of course.